The vast expanse of space has always captured the human imagination. The stars that flicker in the night sky, the distant planets that orbit far from our reach, and the boundless mysteries hidden in the void all beckon us to explore. It's a realm where time stretches, distances are measured in light years, and the laws of physics bend in ways we're only beginning to understand. From ancient stargazers who looked up in wonder, to modern astronauts journeying into the unknown, space has been a constant source of fascination and curiosity. But what exactly is it about the universe that keeps pulling us in? What secrets does the cosmos hold that we've yet to uncover? As we begin this journey through the stars, prepare to be astonished by discoveries that are as mind-bending as they are awe-inspiring. One of the most mind-boggling aspects of space is the sheer scale of it. The distances are almost incomprehensible. Light, which travels at a speed of about 300,000 kilometers per second, still takes more than 8 minutes to reach us from the Sun, a celestial body that is relatively close to Earth in the cosmic sense. Now imagine the nearest star beyond our solar system, Proxima Centauri. It is over 4.24 light-years away. That means even traveling at the speed of light, it would take more than 4 years to reach it. To put that in perspective, if you were flying in a commercial jet at 900 kilometers per hour, it would take you more than 5 million years to get there. This incredible distance is just the tip of the iceberg. The observable universe is estimated to be around 93 billion light-years in diameter. And beyond that lies the unobservable, the part of the universe that we will never be able to see or explore because its light hasn't had enough time to reach us. Among the celestial bodies that fill this vast space, black holes remain one of the most mysterious and awe-inspiring phenomena. These cosmic entities are so dense that not even light can escape their gravitational pull, making them invisible to the naked eye. They form when massive stars collapse under their own gravity at the end of their life cycles. But what's truly remarkable is that black holes aren't just vacuum cleaners sucking up everything around them. They can actually bend space and time. This is a concept called space-time curvature, predicted by Albert Einstein in his theory of general relativity. When a star, planet, or even light itself comes near a black hole, its path warps, creating a strange and almost surreal effect. The most famous black hole, Sagittarius A*, lies at the center of our galaxy and is 4 million times more massive than the Sun. Despite its size, its gravitational influence is so great that time itself slows down the closer you get to it. If you were to hover near the event horizon of a black hole, time would pass slower for you compared to someone far away, meaning that while only a few moments might pass for you, years or even centuries could pass for an observer at a distance. Stars, those luminous points of light scattered across the night sky, have a life cycle of their own, often much more dramatic than we might imagine. Every star, including our Sun, is born from clouds of gas and dust in space. These clouds, under the right conditions, collapse under their own gravity, heating up and eventually igniting nuclear fusion in their cores. This is the process that powers stars, allowing them to shine for millions or even billions of years. But what happens when a star runs out of fuel? The answer depends on the star's size. Smaller stars, like our Sun, will eventually swell into red giants before shedding their outer layers, leaving behind a dense core known as a white dwarf. Larger stars, however, go out with a bang. When they exhaust their nuclear fuel, they explode in a supernova, an event so powerful that it can outshine entire galaxies for a brief period. What's left behind after such an explosion can be a neutron star, an incredibly dense remnant, just a few kilometers across but with the mass of several suns. Or, if the star was massive enough, a black hole. Galaxies, the vast collections of stars, planets, gas, and dust that populate the universe, are another source of endless intrigue. Our own galaxy, the Milky Way, is home to over 100 billion stars and is so vast that even traveling at the speed of light, it would take you 100,000 years to traverse from one end to the other. But the Milky Way is far from the only galaxy out there. In fact, there are more galaxies in the observable universe than there are grains of sand on all the beaches of Earth. The Hubble Space Telescope has captured images of galaxies billions of light-years away, revealing a universe that is both beautiful and chaotic. Galaxies often collide and merge, a process that can take millions of years. Our own Milky Way is on a collision course with the neighboring Andromeda galaxy, and in about 4 billion years, the two will merge to form a new, even larger galaxy. These collisions, though destructive on a local scale, are a natural part of the cosmic cycle and play a key role in galaxy evolution. As we continue to explore the cosmos, we can't ignore the possibility of life beyond Earth. The discovery of exoplanets, planets that orbit stars outside our solar system, has opened up the tantalizing possibility that life may exist elsewhere in the universe. To date, over 5,000 exoplanets have been discovered, and many of them reside in the so-called habitable zone of their stars, where conditions might be right for liquid water to exist, a key ingredient for life as we know it. One of the most intriguing exoplanets is Proxima Centauri b, located just 4.24 light-years away in the habitable zone of its star. Although we have yet to find definitive evidence of life on any of these worlds, the discovery of even microbial life on another planet would revolutionize our understanding of biology and our place in the cosmos. It's worth noting that the building blocks of life, amino acids and other organic molecules, have been found in meteorites and comets, suggesting that the ingredients for life might be common throughout the universe. Our own solar system still holds many secrets, despite being the most explored part of the cosmos. For instance, beneath the icy surface of Jupiter's moon Europa, scientists believe there is a vast ocean of liquid water. This ocean, kept warm by the tidal forces exerted by Jupiter's gravity, could harbor life in its depths, similar to the extremophiles that thrive around hydrothermal vents on Earth. Similarly, Saturn's moon Enceladus has geysers that spew water vapor into space, hinting at the presence of a subsurface ocean as well. Even Mars, once thought to be a barren desert, shows signs that liquid water might have existed on its surface in the past, and recent discoveries of underground lakes suggest that water could still be present today. Time itself behaves differently in space. We often think of time as a constant, but in the realm of relativity, time is far from absolute. It can stretch and compress depending on the gravitational field and the speed at which you're moving. This means that astronauts aboard the International Space Station, traveling at high speeds and experiencing weaker gravity than we do on Earth, age slightly slower than we do. The difference is minuscule, just a fraction of a second over a year, but it's real. The effect becomes much more pronounced in stronger gravitational fields, such as those near black holes or massive planets. This phenomenon, known as time dilation, has been experimentally verified and remains one of the most fascinating predictions of Einstein's theory of relativity. Even light, the fastest thing in the universe, is not immune to the effects of gravity. When light passes near a massive object like a star or galaxy, its path bends, a phenomenon known as gravitational lensing. This effect allows us to see objects that are otherwise hidden behind other celestial bodies. In some cases, gravitational lensing creates multiple images of the same object, and in extreme cases, it can even magnify distant galaxies, allowing astronomers to peer deeper into the universe than ever before. It's through gravitational lensing that we've been able to observe some of the most distant and ancient objects in the universe, providing a glimpse into what the cosmos looked like billions of years ago, shortly after the Big Bang. The mysteries of space are far from fully understood. As our technology advances and we probe deeper into the universe, we're bound to encounter phenomena that challenge our understanding of physics and the natural world. From the potential existence of wormholes, shortcuts through space-time that could theoretically allow faster-than-light travel, to the enigmatic dark matter and dark energy that make up most of the universe's mass, the cosmos is filled with enigmas waiting to be unraveled. One thing is certain. As long as humanity continues to look up at the stars, our journey of discovery will never end. The journey into space never ceases to amaze, as each discovery seems to open new doors to even more profound questions. One of the most elusive mysteries that continues to baffle astronomers and physicists alike is the nature of dark matter and dark energy. These two concepts, though invisible to the human eye and undetectable by traditional means, are believed to make up the vast majority of the universe. In fact, only about 5% of the universe is made up of the regular matter that we can see, such as stars, planets, and galaxies. The remaining 95% consists of dark matter and dark energy, forces that we know very little about, but which exert a massive influence on the structure and expansion of the universe. Dark matter is thought to be a type of matter that doesn't emit, absorb, or reflect light, making it completely invisible. Its existence is inferred from its gravitational effects on visible objects. For instance, galaxies spin much faster than they should based on the amount of visible matter they contain. Without the additional gravitational pull from dark matter, they would fly apart. This invisible substance is like a cosmic glue, holding galaxies together and shaping the large-scale structure of the universe. Despite decades of searching, no one has yet been able to directly detect dark matter, and its composition remains one of the greatest unsolved puzzles in cosmology. Even more mysterious is dark energy, a force that seems to be responsible for the accelerating expansion of the universe. In 1998, astronomers made the shocking discovery that the universe wasn't just expanding, but expanding at an ever-increasing rate. This was completely unexpected because gravity should be slowing down the expansion over time. The only explanation is that some unknown force, dark energy, is pushing galaxies apart at an accelerating pace. Dark energy is thought to make up about 68% of the universe, and yet, like dark matter, we have no idea what it actually is. It's possible that dark energy is a property of space itself, or it could be related to some new, undiscovered force of nature. Whatever the case may be, understanding dark energy is one of the most important goals of modern astrophysics because it will help us understand the ultimate fate of the universe. While dark matter and dark energy stretch the boundaries of what we know about the universe, there are other phenomena that challenge our understanding of time and space in more familiar, yet still perplexing ways. One such phenomenon is the possibility of wormholes. According to Einstein's theory of general relativity, it is theoretically possible for space-time to be warped in such a way that it creates shortcuts through the universe. These are known as wormholes. A wormhole could connect two distant points in space, allowing for faster-than-light travel. However, while the mathematics behind wormholes are sound, we've never observed one. In fact, creating a stable wormhole, if it were possible, would likely require an exotic form of matter with negative energy, something that is yet to be discovered. Even without the need for speculative constructs like wormholes, space itself behaves in ways that seem almost magical. Take, for instance, the twin paradox, a thought experiment based on the principles of special relativity. Imagine that one twin stays on Earth while the other embarks on a journey through space at near light speed. Upon returning, the traveling twin would find that far less time had passed for them compared to their sibling back on Earth. This time dilation effect has been experimentally confirmed, though on a much smaller scale, with atomic clocks flown on aircraft or aboard the International Space Station. While the time difference is minuscule in these cases, it highlights the strange and counterintuitive way that time behaves at relativistic speeds, where the faster you move, the slower time flows for you. Space is also home to some of the most extreme and violent events in the cosmos: supernovae, gamma-ray bursts, and collisions between massive celestial bodies. Supernovae are among the most spectacular events in the universe, occurring when a star explodes at the end of its life. The explosion can be so bright that it temporarily outshines an entire galaxy. These cosmic explosions not only signal the death of a star, but also play a crucial role in the universe's evolution. The elements created in the cores of stars, such as carbon, oxygen, and iron, are spread throughout the cosmos by supernova explosions, seeding the universe with the building blocks of planets and life itself. In fact, every atom in your body was forged in the heart of a star, making us quite literally stardust. Even more extreme than supernovae are gamma-ray bursts, the most energetic events known to occur in the universe. These bursts of gamma rays, the most energetic form of light, can release as much energy in a few seconds as the sun will produce in its entire 10 billion-year lifetime. Gamma-ray bursts are believed to occur when massive stars collapse to form black holes or when neutron stars collide. These events are so powerful that if a gamma-ray burst were to happen too close to Earth, it could strip away the planet's atmosphere and wipe out life as we know it. Fortunately, gamma-ray bursts are rare and typically occur in distant galaxies. The idea of celestial collisions is not limited to gamma-ray bursts. In fact, such collisions are quite common on a cosmic scale. Galaxies themselves frequently merge in slow-motion collisions that can take millions of years to unfold. When galaxies collide, their stars typically pass by each other without colliding due to the vast distances between them, but the gas and dust in the galaxies interact, often triggering bursts of star formation. The collision between the Milky Way and the Andromeda Galaxy, set to occur in about 4 billion years, will be a dramatic event, though it's unlikely to pose a threat to any existing life in our galaxy. The two galaxies will merge to form a new, larger galaxy, reshaping the cosmos as we know it. On a smaller scale, asteroid and comet impacts have had a profound effect on the history of our own planet. The most famous of these impacts occurred about 66 million years ago, when a massive asteroid struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact triggered a mass extinction event, wiping out the dinosaurs and paving the way for mammals, and eventually humans, to dominate the planet. But Earth continues to be vulnerable to impact from space. In fact, thousands of near-Earth objects, asteroids and comets that pass close to our planet, are tracked by astronomers to ensure that we have advance warning of any potential threats. While the chances of a major impact in the near future are low, the possibility remains, and plans are being developed to deflect or destroy hazardous asteroids before they can strike Earth. As we continue to peer deeper into the cosmos, we are constantly reminded of how little we truly know. For every mystery we solve, a new one seems to emerge, keeping the allure of space exploration as strong as ever. Whether it's the search for alien life, the quest to understand the origins of the universe, or the ongoing exploration of our own solar system, humanity's journey into space is just beginning. Each discovery, no matter how small, brings us closer to answering some of the biggest questions ever posed. Are we alone in the universe? What is the fate of the cosmos? And what role will humanity play in the grand story of the universe's future? The answers, if they come, will redefine our understanding of not just the universe, but of ourselves and our place in it. As we continue our exploration of space, one of the most captivating aspects is the ongoing search for extraterrestrial life. For centuries, humans have wondered whether we are alone in the universe, but it's only in recent decades that we've begun to search in earnest. This quest is driven not only by curiosity, but by the discovery of planets orbiting distant stars, exoplanets, that may have the right conditions for life. In 1995, astronomers discovered the first exoplanet around a sun-like star, and since then, thousands more have been found. Many of these planets exist in the habitable zone of their stars, where temperatures could allow for liquid water to exist on the surface. This tantalizing possibility has fueled efforts to detect signs of life beyond Earth, whether through advanced telescopes, robotic missions, or even listening for signals from intelligent civilizations. Among the most promising candidates for life are the moons within our own solar system. Europa, one of Jupiter's largest moons, has captured the attention of scientists because of its icy surface, which hides a vast ocean of liquid water beneath. This ocean, kept warm by the gravitational forces exerted by Jupiter, could be similar to the hydrothermal environments on Earth, where life thrives in extreme conditions. NASA's upcoming Europa Clipper mission is set to investigate this moon in greater detail, searching for signs of habitability. Similarly, Saturn's moon Enceladus has geysers that spew water vapor and organic molecules into space, suggesting the presence of an ocean beneath its icy crust. Both moons are considered prime targets in the search for extraterrestrial life, and future missions may one day send probes to drill through the ice and explore their hidden oceans. Mars, the red planet, has long been a focus of the search for life beyond Earth. While the surface of Mars today is cold and dry, there is strong evidence that liquid water once flowed across its surface. River valleys, lake beds, and mineral deposits that form in the presence of water point to a time billions of years ago when Mars had a much thicker atmosphere and a more Earth-like climate. If life ever existed on Mars, it may have left behind fossils or other traces that scientists are eager to find. NASA's Perseverance rover, which landed on Mars in 2021, is actively searching for signs of ancient microbial life in a region that once contained a lake. Perseverance is also collecting samples that will eventually be returned to Earth, where they can be analyzed in greater detail than is possible with instruments on the Martian surface. Beyond our solar system, the discovery of exoplanets has revolutionized our understanding of the universe and its potential to harbor life. The sheer diversity of planets that have been found is staggering, ranging from gas giants like Jupiter to rocky worlds similar in size to Earth. Some exoplanets orbit so close to their stars that their surfaces are scorched by intense heat, while others are located in the habitable zone where liquid water could exist. One of the most famous of these is Proxima Centauri b, a planet orbiting the star closest to our solar system, just over 4 light-years away. While it resides in its star's habitable zone, the conditions on Proxima Centauri b may be too extreme for life as we know it, due to the star's frequent solar flares and harsh radiation. The search for life extends beyond planets and moons. Some scientists speculate that life could exist in environments we once thought were completely inhospitable, such as the upper atmospheres of gas giants like Jupiter or even in the clouds of Venus. In 2020, researchers announced the detection of phosphine, a gas that on Earth is produced by microbial life, in the atmosphere of Venus. This discovery, though still under debate, has reignited interest in Venus, a planet once dismissed as too hostile for life due to its scorching surface temperatures and crushing atmospheric pressure. If microbial life does exist in the clouds of Venus, it would challenge many of our assumptions about where life can survive. As exciting as the search for microbial life is, the possibility of intelligent extraterrestrial civilizations continues to captivate the imagination. The idea that we might one day make contact with an advanced alien species has inspired countless works of science fiction, but it also raises profound scientific and philosophical questions. For decades, scientists have been listening for signals from other civilizations through programs like SETI, Search for Extraterrestrial Intelligence. These efforts involve using radio telescopes to scan the skies for transmissions that might be coming from distant stars. So far, no definitive signals have been detected, but the search continues, with new technologies allowing us to scan more of the sky and detect fainter signals than ever before. One of the key challenges in the search for intelligent life is understanding how to recognize a signal if we ever receive one. An alien civilization's communication methods might be so different from our own that we wouldn't immediately recognize it as artificial. Moreover, the vast distances between stars mean that any signals we receive could be thousands of years old by the time they reach us. This means that even if a civilization sent out a message, it could have long since vanished by the time we hear it. These challenges haven't deterred scientists, though, who remain hopeful that one day we may detect a signal that confirms we are not alone. While the search for extraterrestrial life often focuses on far-off planets and stars, Earth itself may hold clues about the likelihood of life elsewhere in the universe. The study of extremophiles, organisms that thrive in some of the most extreme environments on Earth, has expanded our understanding of the conditions under which life can exist. These organisms live in environments previously thought to be uninhabitable, such as deep-sea hydrothermal vents, acidic hot springs, and even within rocks several kilometers beneath the Earth's surface. The discovery of life in these extreme environments suggests that life might be more adaptable and resilient than we once thought, increasing the chances that it could exist in the harsh environments of other planets or moons. In addition to searching for life beyond Earth, scientists are also trying to understand how life first emerged here. The origin of life on Earth remains one of the biggest unsolved mysteries in science. While we have a good understanding of how life evolved once it appeared, the question of how the first living organisms came into being is still hotly debated. One leading hypothesis is that life began in hydrothermal vents on the ocean floor, where mineral-rich water provides the energy needed to drive chemical reactions. Another possibility is that life's building blocks arrived from space, delivered by comets or meteorites. In fact, some meteorites have been found to contain amino acids and other organic molecules, supporting the idea that life's ingredients may be common throughout the universe. If life does exist elsewhere in the universe, whether microbial or intelligent, the discovery would have profound implications for humanity. It would not only transform our understanding of biology and evolution, but it would also force us to reconsider our place in the cosmos. Are we just one of many intelligent civilizations scattered across the stars? Or is life exceedingly rare? making us unique in the universe? These questions may take centuries to answer, or we might find the answers sooner than we expect as our technology advances and our exploration of space continues. The discovery of life beyond Earth would also raise ethical and philosophical questions about how we should interact with extraterrestrial life forms, should we ever encounter them. If we discover microbial life on Mars or Europa, for example, should we study it or leave it undisturbed? And if we ever make contact with an intelligent alien civilization, how should we communicate? And what should we say? These are questions that humanity will need to grapple with as our exploration of space moves forward. As we venture further into the cosmos, the search for life beyond Earth will remain one of the most exciting and important areas of exploration. With each new mission, telescope, and discovery, we come closer to answering the age-old question: are we alone in the universe? Whether we find life on a distant planet, beneath the icy surface of a moon, or in the atmosphere of a distant star, the discovery will change the course of human history, opening up a new chapter in our understanding of the universe and our place within it. As we delve deeper into the mysteries of space, one of the most astonishing discoveries has been the revelation that the universe is not static, but constantly expanding. This groundbreaking finding, first proposed by Edwin Hubble in 1929, forever changed our understanding of the cosmos. Using a powerful telescope, Hubble observed that distant galaxies appeared to be moving away from us, with their light shifting toward the red end of the spectrum, an effect known as redshift. This observation led to the realization that the universe is expanding in all directions, like the surface of an inflating balloon. The implications of this are profound. If the universe is expanding now, then it must have been smaller in the past, suggesting that everything we see today once originated from a single point in space and time. This theory, now known as the Big Bang, describes the birth of the universe approximately 13.8 billion years ago. The Big Bang theory is supported by multiple lines of evidence, including the discovery of the cosmic microwave background radiation, CMB. In 1965, scientists Arno Penzias and Robert Wilson stumbled upon a faint background noise in their radio telescope, which turned out to be the afterglow of the Big Bang, radiation left over from the universe's infancy. This ancient light, which has been traveling through space for nearly 14 billion years, provides a snapshot of the universe when it was just 380,000 years old. Studying the CMB allows scientists to peer back in time, gaining insights into the early moments of the cosmos, when matter and energy were still tightly packed together before galaxies, stars, and planets began to form. As remarkable as the Big Bang theory is, it also raises profound questions. What existed before the Big Bang? What caused it? These are questions that lie at the frontier of modern physics. And though we don't yet have definitive answers, several hypotheses have been proposed. One idea is that the Big Bang was not the beginning of everything, but rather a transition between different phases of the universe. In this view, our universe could be part of a larger multiverse, an infinite collection of universes, each with its own set of physical laws. Some theories even suggest that universes are constantly being created and destroyed, a process known as the Big Bounce, where each universe expands and then contracts in a cycle of birth and death. The concept of a multiverse, while speculative, is supported by certain interpretations of quantum mechanics and string theory, two of the most advanced areas of theoretical physics. String theory, for instance, posits that the fundamental building blocks of the universe are not particles like electrons or quarks, but tiny, vibrating strings of energy. These strings vibrate at different frequencies, creating the various particles and forces we observe. According to some versions of string theory, our universe may be just one of many that exist in a higher dimensional space. Each of these universes could have different properties. Some might have different numbers of dimensions, while others might have different laws of physics altogether. This idea of parallel universes is tantalizing because it opens up the possibility that our universe is just one small part of a much larger, more complex reality. If the multiverse exists, then there could be other versions of you, living in alternate universes where the events of your life played out differently. There could be universes where different physical constants led to the formation of entirely alien forms of matter and life. While this idea sounds like science fiction, It's a legitimate area of scientific inquiry, and future discoveries in quantum mechanics and cosmology may one day provide evidence to support or refute the existence of the multiverse. Back within our own universe, one of the most perplexing discoveries of recent years is the phenomenon of cosmic inflation. According to this theory, the universe underwent a brief but extremely rapid expansion just moments after the Big Bang, growing from a subatomic scale to a macroscopic size in less than a trillionth of a second. This period of inflation explains several puzzling aspects of the universe, such as its large-scale uniformity and the fact that regions of the universe that are now vastly separated by billions of light-years appear to have the same temperature and density. Without inflation, these regions would never have been in contact with each other, so the fact that they are so similar in structure suggests that they were once much closer together. The inflationary model of the universe also predicts the existence of quantum fluctuations in the fabric of space-time during this rapid expansion. These tiny fluctuations, though minuscule at the time, were stretched to enormous sizes by inflation and eventually gave rise to the large-scale structure of the universe we see today. Clusters of galaxies, voids, and filaments that stretch across the cosmos. Inflation theory has been remarkably successful in explaining these features of the universe, but it also suggests that inflation may still be occurring in some regions of space, potentially giving rise to new universes in the multiverse. Another fascinating consequence of the expanding universe is the eventual fate of everything within it. As galaxies continue to move farther apart, driven by the mysterious force of dark energy, the universe will become colder and more isolated over time. This scenario, known as the Big Freeze or heat death, predicts that the universe will continue expanding until all stars burn out, black holes evaporate, and the remaining matter is spread so thin that no new stars or planets can form. In this bleak future, the universe would be a dark, cold, and lifeless place, with all sources of energy eventually fading away. However, other potential endings for the universe have been proposed. One possibility is the Big Crunch, in which the expansion of the universe eventually reverses, causing galaxies to collapse back in on themselves. In this scenario, the universe would end in a fiery cataclysm, with all matter and energy crushed into a singular point, much like the Big Bang in reverse. Another idea is the Big Rip, in which dark energy becomes so powerful that it tears apart not just galaxies, but also stars, planets, and even atoms themselves, causing the universe to disintegrate into a sea of fundamental particles. Though these ideas may seem distant and abstract, they underscore the fact that the universe is dynamic and constantly evolving, with a future that is still uncertain. But while the long-term fate of the cosmos may be beyond our control, humanity's exploration of space has opened up incredible opportunities for discovery and innovation. The development of space travel has allowed us to send robotic probes to distant planets, land humans on the moon, and even begin planning for missions to Mars. These achievements represent just the beginning of what could be a new era of space exploration, one in which humanity ventures beyond the confines of Earth to become a truly interplanetary species. One of the most ambitious goals of modern space exploration is the colonization of other planets. Mars, with its relatively accessible surface and evidence of past liquid water, has emerged as the prime candidate for human settlement. Several space agencies, including NASA, the European Space Agency, ESA, and private companies like SpaceX, are actively working on plans to send humans to Mars within the next few decades. The challenges are immense. Mars has a thin atmosphere, extreme temperatures, and high levels of radiation, but technological advances in space habitats, life support systems, and propulsion could make human colonies on Mars a reality in the not-too-distant future. Establishing a permanent presence on Mars or other celestial bodies would not only ensure the survival of humanity in the event of a catastrophe on Earth, but it would also allow us to conduct scientific research on an unprecedented scale. By studying Mars up close, we could learn more about the planet's geological history, search for signs of past or present life, and even begin terraforming, altering the environment to make it more Earth-like. While the idea of terraforming may sound like science fiction, scientists are already considering ways to warm Mars' atmosphere, such as releasing greenhouse gases to trap heat, which could eventually create conditions suitable for liquid water and possibly even plant life. In addition to Mars, the outer solar system offers intriguing possibilities for future exploration. Jupiter's moon Europa, with its subsurface ocean, could harbor life, while Saturn's moon Titan, with its thick atmosphere and lakes of liquid methane, presents a unique environment unlike anything found on Earth. The exploration of these distant worlds, whether by robotic missions or eventually by human explorers, could provide us with new insights into the nature of life, the formation of planetary systems, and the broader dynamics of the universe itself. As we look to the future, it's clear that the possibilities for space exploration are vast and exciting. From understanding the origins of the universe to searching for life on other planets, the study of space continues to push the boundaries of human knowledge and imagination. With each new discovery, we gain a deeper appreciation for the complexity and beauty of the cosmos. And with each step into the unknown, we come closer to unlocking the secrets of the universe. The future of space exploration is more than just a distant dream. It is actively unfolding before our eyes. As we continue to develop advanced technologies and probe deeper into the cosmos, we are witnessing a new space age emerge, one driven not only by governments and national space agencies, but also by private companies with ambitious goals. This shift is bringing space exploration closer to everyday people, with potential impacts that could reshape human society. The commercialization of space, led by companies like SpaceX, Blue Origin, and others, is transforming what was once the exclusive domain of state-sponsored missions into a competitive and innovative industry. These companies are pioneering reusable rockets, reducing the cost of space travel, and even laying the groundwork for future human colonies on other planets. Space tourism, lunar bases, and even asteroid mining are becoming real possibilities, with profound implications for our future. One of the most transformative developments in this new era is the concept of space tourism. While only a handful of people have ever traveled to space, that number is expected to grow dramatically in the coming decades. Companies like SpaceX, Blue Origin, and Virgin Galactic are already offering suborbital flights, where passengers can experience a few minutes of weightlessness and see the curvature of the Earth from the edge of space. These trips, once reserved for highly trained astronauts, will soon be available to wealthy tourists willing to pay a premium for the experience. As technology improves and the cost of space travel decreases, it's possible that space tourism could become accessible to a broader audience, opening the door to a new type of adventure travel. Beyond short suborbital trips, there are even plans for private missions to orbit the Earth and beyond. SpaceX has announced its intention to send private citizens on a mission around the moon, a journey that hasn't been made since the Apollo program in the 1960s and 70s. This mission, known as Dear Moon, is being funded by Japanese billionaire Yusaku Maezawa, who plans to take a group of artists and creators on a week-long journey around the moon, hoping to inspire new works of art based on the experience. This represents a bold step forward, not just for space tourism, but for the idea of integrating human creativity and exploration in space. While space tourism offers excitement for individuals, the long-term goal of space agencies and private companies alike is to establish a permanent human presence beyond Earth. The moon is once again at the forefront of this ambition. NASA's Artemis program aims to return humans to the lunar surface by 2025, with the goal of establishing a sustainable presence on the moon by the end of the decade. The Artemis missions will not only explore new regions of the moon, such as the South Pole, where water ice is believed to exist in permanently shadowed craters, but also lay the foundation for future missions to Mars. Lunar bases could serve as stepping stones for deeper space exploration, providing a testing ground for technologies and life support systems that will be crucial for longer-duration missions. Living on the moon presents many challenges, from extreme temperature fluctuations to the lack of atmosphere and radiation protection. However, scientists are already working on solutions. For instance, lunar habitats could be built using materials found on the moon itself, such as regolith, which can be 3D printed into structures. These habitats would need to be well insulated to protect astronauts from the harsh environment, and they might be buried underground or covered with thick layers of lunar soil to shield against radiation. Advances in life support systems, such as recycling water and air, will also be crucial for sustaining long-term missions on the moon. One of the most exciting prospects for future lunar exploration is the possibility of mining resources on the moon. Water ice, which is found in the permanently shadowed craters at the lunar poles, could be mined and converted into drinking water, breathable oxygen, or hydrogen fuel for rockets. This concept, known as in situ resource utilization (ISRU), could dramatically reduce the cost of future missions by allowing astronauts to live off the land, rather than relying on supplies from Earth. The moon's surface also contains valuable metals and minerals, including rare earth elements that are crucial for modern technology. In the future, lunar mining operations could provide a new source of raw materials for industries back on Earth, as well as for building infrastructure in space. As the moon becomes more accessible, attention is also turning to Mars, the next great frontier for human exploration. Unlike the moon, Mars has a thin atmosphere and signs of liquid water in its past, making it a more Earth-like environment, though still incredibly harsh. The idea of sending humans to Mars has captured the public's imagination for decades, and now it is closer than ever to becoming a reality. NASA, SpaceX, and other organizations are working on plans to send the first humans to Mars within the next 2 decades, with SpaceX's Starship vehicle being developed specifically for this purpose. Landing humans on Mars would be an extraordinary achievement, but establishing a permanent colony there presents even greater challenges. Mars is much farther from Earth than the Moon, with a journey taking several months, and its thin atmosphere offers little protection from cosmic radiation. The surface is cold and barren, with temperatures averaging -60 degrees Celsius, -80 degrees Fahrenheit, and dust storms that can last for weeks or even months. Despite these obstacles, scientists and engineers are actively developing the technologies needed to make a Mars colony possible. These include advanced spacesuits, radiation-shielded habitats, and sustainable agricultural systems that could grow food in Martian soil, perhaps with the help of genetically modified crops or hydroponics. The long-term vision for Mars is not just to send humans for exploration, but to eventually terraform the planet, transforming its environment to make it more hospitable to life. While this idea remains speculative, some scientists believe it could be possible to warm Mars by releasing greenhouse gases into the atmosphere, creating a thicker atmosphere that could trap heat and potentially support liquid water on the surface. Others have proposed using giant mirrors in space to reflect sunlight onto the planet's poles, melting the ice caps and releasing carbon dioxide to thicken the atmosphere. While these ideas are still in the realm of science fiction, the dream of turning Mars into a second Earth continues to inspire scientists and space enthusiasts alike. The potential benefits of colonizing Mars and other planets are immense. Not only would it ensure the survival of humanity in the event of a catastrophe on Earth, but it could also provide new opportunities for scientific research and technological innovation. A Mars colony could serve as a base for exploring the rest of the solar system, including the moons of Jupiter and Saturn, which may harbor subsurface oceans and the potential for life. It could also become a hub for industries that require large amounts of energy or space, such as asteroid mining, manufacturing, or even energy production through solar power. Asteroid mining, in particular, is seen as one of the most promising industries of the future. Asteroids contain vast quantities of valuable metals, including gold, platinum, and rare earth elements, which are critical for electronics, renewable energy technologies, and other advanced industries. Some asteroids are thought to be worth trillions of dollars in raw materials, and mining them could provide a virtually unlimited supply of resources for humanity. Companies like Planetary Resources and Deep Space Industries have already begun exploring the feasibility of asteroid mining, though the technology to actually extract and return materials from asteroids is still in the early stages of development. The benefits of asteroid mining go beyond just resource extraction. It could also provide a way to protect Earth from dangerous impacts. Near-Earth asteroids, some of which are large enough to cause significant damage if they collided with our planet, are regularly monitored by astronomers. In the future, mining technologies could be used to deflect potentially hazardous asteroids, preventing catastrophic impacts and ensuring the safety of our planet. As we look further into the future, the idea of humanity becoming a multi-planetary species no longer seems like a distant dream. Advances in space travel, robotics, artificial intelligence, and other technologies are bringing this vision closer to reality. Colonies on the Moon, Mars, and perhaps even the moons of the outer planets could one day be self-sustaining, with industries, agriculture, and scientific research thriving in environments once thought too hostile for life. Space travel itself could become as routine as air travel is today, with spacecraft ferrying passengers and cargo between Earth, space stations, and distant colonies. Yet with all the possibilities of space exploration come new challenges and ethical questions. As we expand into space, we must consider how to manage resources sustainably, avoid contaminating other planets with Earth-based organisms, and ensure that space exploration benefits all of humanity, not just a privileged few. The prospect of mining asteroids or establishing colonies on other planets raises questions about ownership, governance, and the responsibility to protect both Earth and the environments we encounter in space. As humanity takes its first steps into this new era of space exploration, we are reminded that the cosmos holds infinite possibilities. From exploring distant planets to unraveling the mysteries of the universe's origin, the quest for knowledge and discovery drives us forward. The future of space exploration is bright, filled with challenges, triumphs, and new horizons waiting to be explored. And as we continue to push the boundaries of what is possible, one thing is certain: our journey into the stars has only just begun. As humanity pushes further into the cosmos, the question of how we will sustain ourselves in space for long periods becomes critical. The conditions in space are hostile. There's no breathable atmosphere, extreme temperature fluctuations, and cosmic radiation that poses serious health risks. For astronauts, long-duration missions present significant physical and psychological challenges. But innovative solutions are being developed to address these issues and to make living in space, whether on a space station, the Moon, or Mars, not only possible but sustainable. One of the primary concerns for space missions is the need for life support systems that can provide air, water, and food. Current missions, like those aboard the International Space Station, ISS, rely on supplies sent from Earth. However, for missions to more distant destinations like Mars, resupplying from Earth is not feasible due to the vast distances and high costs. This is where closed-loop life support systems come in. These systems recycle air, water, and waste to minimize the need for external resources. For example, on the ISS, water is recycled from sweat, urine, and condensation. The station also has systems that filter carbon dioxide out of the air and replace it with oxygen produced through the electrolysis of water. As we look ahead to future missions, these systems will need to be improved and expanded to support larger crews and longer stays. Food is another critical aspect of long-term space missions. Currently, astronauts eat pre-packaged, freeze-dried meals, but this approach won't work for extended missions or colonies. Growing food in space is a complex challenge due to the lack of gravity and the need for controlled environments. However, scientists are already experimenting with space farming. On the ISS, astronauts have successfully grown lettuce and other small crops in hydroponic systems, where plants grow without soil, using nutrient-rich water instead. The ability to grow food in space is a crucial step towards self-sufficiency and would reduce the need for resupply missions from Earth. Mars presents even greater challenges for agriculture, as the planet has a thin atmosphere and extremely cold temperatures. One solution could involve creating greenhouses that use artificial lighting and controlled climates to grow crops. Additionally, research is being conducted on how to use Martian soil, which contains many of the nutrients plants need to grow food. However, Martian soil also contains toxic chemicals called perchlorates, which would need to be removed before it could be used for farming. Genetic engineering could also play a role in developing crops that can thrive in low-light, low-gravity environments. The psychological well-being of astronauts is another major concern for long-duration missions. The isolation, confinement, and distance from Earth can take a toll on mental health. Astronauts aboard the ISS deal with this by maintaining regular contact with their families and mission control, as well as following strict exercise and work schedules to keep their bodies and minds active. However, on missions to Mars, where there could be a communication delay of up to 24 minutes each way, maintaining this connection will be more difficult. Psychological support will become even more critical on long missions, and there is ongoing research into how to create environments that help mitigate the stress of isolation. such as virtual reality systems that simulate outdoor spaces on Earth. Radiation exposure is perhaps one of the most serious health risks for astronauts. In space, there is no protective atmosphere or magnetic field to shield humans from cosmic radiation, which increases the risk of cancer and other health issues. On long missions, especially those to Mars, astronauts would be exposed to much higher levels of radiation than they are on the ISS or the Moon. Researchers are working on several strategies to protect astronauts, including better shielding for spacecraft and habitats, and even developing medications that could protect cells from radiation damage. On Mars, habitats might need to be built underground or covered with thick layers of Martian soil to provide adequate protection. As we consider the logistics of living and working in space, the role of robots and artificial intelligence, AI, will be crucial. Robots are already a key part of space exploration. For instance, NASA's Mars rovers, such as Perseverance and Curiosity, are exploring the surface of Mars and conducting scientific experiments. In the future, robots could be used to build habitats on the Moon or Mars before humans even arrive. They could mine local materials, construct shelters, and set up life support systems. Robots would not only make these missions safer by reducing the need for humans to be exposed to dangerous environments, but they could also operate continuously without needing breaks. AI will also play a critical role in managing life support systems, navigation, and communication. On long-duration missions, where real-time communication with Earth is not possible, AI systems could assist astronauts in making decisions, diagnosing problems, and conducting scientific research. AI could also be used to analyze vast amounts of data collected from space missions, helping to identify patterns and insights that humans might miss. Space habitats themselves will need to be designed with the harsh environment of space in mind. In the vacuum of space, or on a planet like Mars, where there is no breathable atmosphere, structures will need to be airtight and highly insulated to protect against extreme temperatures and radiation. Inflatable habitats are one possible solution. These structures are compact and lightweight, making them easier to transport, and can be inflated once they reach their destination to create a livable space. NASA has already tested inflatable modules on the ISS, such as the Bigelow Expandable Activity Module beam, which demonstrates how these habitats could be used for future missions. Looking even further into the future, some scientists have proposed the idea of building large space habitats that orbit the Earth or other celestial bodies. These structures, sometimes called space stations or O'Neill cylinders, would be massive, rotating cylinders that create artificial gravity through centrifugal force. Inside these habitats, people could live, work, and even grow food in a controlled environment. These space stations could serve as hubs for space travel, allowing humans to live and work in space without the need to constantly travel back and forth to Earth. One of the most fascinating ideas being explored is the concept of space elevators. A space elevator would be a cable stretching from Earth's surface to a point in geostationary orbit, allowing spacecraft to travel up and down the cable instead of using rockets. This could dramatically reduce the cost of sending materials and people into space, making space travel more accessible. While the technology to build a space elevator is still in its infancy, recent advances in materials science, such as the development of carbon nanotubes, are bringing the concept closer to reality. As space exploration advances, the ethical implications of our actions in space will also become increasingly important. For example, the discovery of life on other planets, even in microbial form, would raise significant ethical questions. Should we study these life forms, or should we leave them undisturbed to avoid contaminating their ecosystems? How should we protect the environments of other planets, moons, and asteroids as we explore and potentially exploit their resources? Moreover, the expansion of human presence into space will bring new challenges related to governance and regulation. Currently, space is considered a global commons, governed by treaties like the Outer Space Treaty of 1967, which prohibits the militarization of space and claims of sovereignty over celestial bodies. However, as private companies and nations begin to explore and develop space for commercial purposes, new legal frameworks will be needed to address issues such as property rights, resource extraction, and the management of space traffic. One of the biggest unknowns in space exploration is the potential for human encounters with extraterrestrial intelligence. While the search for intelligent life has yet to yield results, it remains one of the most exciting and profound questions of our time. If we were to discover an advanced alien civilization, how would we communicate with them? What would be the cultural, political, and ethical implications of such an encounter? These are questions that humanity will need to grapple with as we continue our journey into the cosmos. In many ways, space exploration is a mirror of human ambition. It represents our desire to understand the universe and our place in it, to push the boundaries of what is possible, and to ensure the survival and flourishing of our species. As we look to the future, the possibilities seem endless. The colonization of the Moon, Mars, and beyond may not happen overnight, but each step we take brings us closer to a future where humanity is no longer confined to Earth. The dream of living among the stars has been a part of human imagination for millennia, and now, for the first time in history, we have the technology and knowledge to make that dream a reality. With each new discovery, whether it's a new planet, a groundbreaking technology, or an insight into the nature of the universe itself, we move closer to realizing our destiny as explorers of the cosmos. The journey will be long, and the challenges immense, but the rewards, a deeper understanding of the universe, new opportunities for growth, and the possibility of life beyond Earth, are more than worth the effort. The stars await us, and humanity's future is brighter than ever. As humanity stands on the brink of becoming an interplanetary species, the possibilities for future exploration and discovery are both thrilling and daunting. One of the most exciting prospects for the near future is the continued exploration of our solar system's outer planets and their moons. While much of our attention has been focused on Mars and the Moon, the outer planets, Jupiter, Saturn, Uranus, and Neptune, along with their diverse and intriguing moons, hold many secrets that could reshape our understanding of the solar system and perhaps even reveal new clues about the origins of life. Among these moons, Europa, one of Jupiter's largest, is particularly compelling. Scientists believe that beneath its icy surface lies a vast ocean of liquid water, kept warm by tidal forces from Jupiter's immense gravity. This ocean, potentially containing more water than all of Earth's oceans combined, could harbor life. The Europa Clipper mission, set to launch in the 2020s, will conduct detailed reconnaissance of Europa's surface and subsurface, searching for signs of habitability and studying the chemistry of its ice and water. If life exists in Europa's ocean, it could take the form of microbial organisms similar to those found in Earth's deep-sea hydrothermal vents, places where life thrives despite the lack of sunlight. The discovery of even the simplest forms of life on Europa would profoundly change our understanding of biology and life's potential to arise in environments far different from our own. Similarly, Saturn's moon Titan presents a tantalizing target for exploration. Titan is unique in the solar system because it has a thick atmosphere, composed mostly of nitrogen, and lakes and rivers of liquid methane and ethane on its surface. While the chemistry of Titan's environment is vastly different from Earth's, some scientists believe that it could support a form of life that is based on methane rather than water. The Dragonfly mission, a planned NASA mission set to launch in the 2030s, will send a rotorcraft to explore Titan's diverse surface, flying to different locations to study its organic chemistry, surface composition, and potential for habitability. The mission could reveal new insights into the kinds of chemistry that can occur on other worlds, and whether life could exist in environments that are radically different from those on Earth. Beyond the moons of Jupiter and Saturn, the ice giants Uranus and Neptune remain largely unexplored, with only a single flyby from the Voyager 2 spacecraft in the late 1980s. These planets are shrouded in mystery, and their complex atmospheres and unusual magnetic fields present many puzzles for scientists. Both planets have rings, dynamic weather systems, and multiple moons, some of which may have oceans beneath their icy crusts. Future missions to these distant worlds could unlock new information about how planets form, how their weather systems work, and what their interiors are made of. In particular, studying their icy moons, such as Neptune's Triton, which is believed to have active geysers and a subsurface ocean, could yield exciting discoveries about the potential for life in the far reaches of the solar system. As we look beyond our solar system, the next major frontier in space exploration is the study of exoplanets, planets that orbit stars other than our Sun. Since the first exoplanet was discovered in 1995, thousands of these worlds have been identified, with some located in the habitable zones of their stars, where conditions might be right for liquid water and possibly life. The search for Earth-like exoplanets has been greatly accelerated by advanced space telescopes, such as NASA's Kepler and TESS missions, which have scanned the skies for signs of planets transiting in front of their host stars. These observations have revealed a staggering diversity of planets, including hot Jupiters, super-Earths, and mini-Neptunes, some of which defy current models of planetary formation. The James Webb Space Telescope, JWST, launched in 2021, has further revolutionized our ability to study these distant worlds. With its powerful infrared capabilities, JWST is able to observe the atmospheres of exoplanets, looking for key molecules like water vapor, carbon dioxide, and methane, potential indicators of life. One of the telescope's primary goals is to study the atmospheres of planets and the habitable zones of nearby stars, searching for biosignatures that might suggest the presence of life. The detection of such signals would be a monumental breakthrough, providing the first evidence that we are not alone in the universe. As we improve our ability to detect and study exoplanets, we are also beginning to contemplate the possibility of sending spacecraft to explore them directly. While the distances to even the nearest stars are immense, concepts like Breakthrough Starshot offer a glimpse of how we might one day reach these distant worlds. Breakthrough Starshot is an ambitious project that aims to send tiny, light-powered spacecraft to the Alpha Centauri system, the nearest star system to our own, located about 4.24 light-years away. These spacecraft, equipped with cameras and sensors, would be propelled by powerful lasers from Earth, traveling at a significant fraction of the speed of light. If successful, they could reach Alpha Centauri in just over 20 years, providing humanity's first close-up images of another star system and its planets. The search for life beyond Earth continues to drive many aspects of space exploration, but the pursuit of understanding goes even further. One of the most profound mysteries that scientists are attempting to solve is the nature of dark matter and dark energy, two components that make up about 95% of the universe, yet remain largely invisible and poorly understood. Dark matter, which makes up about 27% of the universe, doesn't interact with light, making it impossible to detect directly. However, its presence is inferred through its gravitational effects on visible matter, such as stars and galaxies. Without dark matter, galaxies would not have enough mass to hold themselves together, and the large-scale structure of the universe would be vastly different. Dark energy, on the other hand, is even more mysterious. It is believed to be the force driving the accelerated expansion of the universe, accounting for about 68% of the universe's total energy content. The discovery that the universe is expanding at an increasing rate was made in the late 1990s and shocked scientists, who had expected the expansion to slow over time due to the pull of gravity. Dark energy seems to work in the opposite way, causing galaxies to move apart faster and faster. Understanding dark energy is one of the greatest challenges in modern physics, and solving this mystery could lead to a revolution in our understanding of the cosmos and the fundamental forces that govern it. In the search for answers, scientists are turning to ever more powerful telescopes and experiments. The Vera C. Rubin Observatory, set to begin operations soon, will survey the sky with unprecedented depth and detail, mapping billions of galaxies to better understand the distribution of dark matter and the effects of dark energy. Meanwhile, particle physics experiments like those at the Large Hadron Collider, LHC, are probing the nature of dark matter by smashing subatomic particles together at high speeds, hoping to produce particles that could explain its mysterious properties. The ongoing study of gravitational waves, ripples in the fabric of space-time caused by the collision of massive objects like black holes, has also opened up a new window on the universe. First detected in 2015 by the LIGO experiment, gravitational waves have provided a new way to observe events in the cosmos that are otherwise invisible to traditional telescopes. In the future, space-based observatories like the Laser Interferometer Space Antenna, LISA, will be able to detect gravitational waves from even more distant and massive objects, helping scientists to study the formation of black holes, neutron stars, and perhaps even the earliest moments after the Big Bang. As we explore these mysteries, one question looms above all others. What is the ultimate fate of the universe? While the Big Bang marked the universe's beginning, its future remains uncertain. Will the universe continue expanding forever, slowly cooling and fading into darkness in a scenario known as the Big Freeze? Or will the expansion eventually reverse, leading to a big crunch, where everything collapses back into a singular point? Some theories even propose the possibility of a big rip, where the expansion of the universe accelerates to such an extent that galaxies, stars, planets, and eventually even atoms are torn apart by the fabric of spacetime itself. While these cosmic questions may seem distant from everyday life, they represent the cutting edge of human knowledge and curiosity. As we continue to unlock the secrets of the universe, we are constantly reminded of how much more there is to learn. The journey of exploration, whether through the study of exoplanets, the search for dark matter, or the observation of gravitational waves, reflects our deep desire to understand the cosmos and our place within it. Each new discovery brings us one step closer to answering the fundamental questions that have driven humanity for millennia. How did we get here? What is the nature of the universe? And where are we going? As we look to the future, the possibilities for exploration, discovery, and innovation are endless. The stars beckon, and humanity's journey into the cosmos is only just beginning. As humanity ventures deeper into space, the concept of interstellar travel, a dream once confined to science fiction, has begun to capture the imagination of scientists and engineers in more tangible ways. Traveling to distant star systems presents challenges that are orders of magnitude greater than anything we have faced so far. The vast distances between stars, often measured in light years, mean that even with the fastest spacecraft we currently have, it would take tens of thousands of years to reach our nearest stellar neighbors. Despite these seemingly insurmountable obstacles, new technologies and theoretical concepts are being explored that could one day make interstellar travel possible, opening up a whole new chapter in the exploration of the universe. One of the most promising ideas being developed is the concept of light sails or solar sails. These sails are large, ultra-thin sheets of reflective material that can be propelled through space by the pressure of photons, particles of light, emitted by the sun or powerful lasers. This form of propulsion does not require fuel, which makes it ideal for long-duration missions where carrying massive amounts of propellant would be impractical. The idea of solar sails has been around for decades, but recent advances in materials science and laser technology have brought it closer to reality. The Breakthrough Starshot Initiative, for instance, is working on developing tiny spacecraft equipped with light sails that could be propelled by powerful Earth-based lasers to speeds of up to 20% the speed of light. At that velocity, these spacecraft could reach the Alpha Centauri system, just over 4 light-years away, in about 20 years. While Breakthrough Starshot spacecraft would be too small to carry humans, the technology could pave the way for future missions that might one day send larger, crewed vessels to other star systems. Other forms of propulsion, such as nuclear fusion engines, antimatter propulsion, and even theoretical concepts like the warp drive, are being studied as potential ways to shorten the travel time between stars. Fusion propulsion, for example, would harness the same energy that powers the sun by fusing hydrogen atoms into helium, releasing massive amounts of energy. A spacecraft powered by fusion could potentially reach speeds much higher than those achievable with current chemical rockets, reducing the time to travel between stars from thousands of years to decades or centuries. Antimatter propulsion, while still purely theoretical, offers even greater potential. When matter and antimatter collide, they annihilate each other in a burst of energy, releasing far more power than any conventional fuel source. If we could harness antimatter as a fuel, it could provide the energy needed to push spacecraft to relativistic speeds, approaching the speed of light. However, producing and storing antimatter is an enormous technological challenge. Currently, we can only create tiny amounts of antimatter in particle accelerators, and storing it safely for extended periods is still beyond our reach. But as technology advances, these challenges may one day be overcome, potentially unlocking the key to interstellar travel. Perhaps the most speculative of all the ideas for interstellar travel is the concept of a warp drive, which would allow a spacecraft to travel faster than the speed of light, by warping the fabric of spacetime itself. This idea was popularized by science fiction, particularly Star Trek, but it is grounded in real physics, particularly Albert Einstein's theory of general relativity. The concept involves creating a bubble of spacetime around a spacecraft and contracting space in front of the ship while expanding it behind, effectively moving the spacecraft without violating the laws of physics that prevent anything from traveling faster than light. In 1994, physicist Miguel Alcubierre proposed a theoretical model for such a drive, now known as the Alcubierre drive, but it would require vast amounts of energy, potentially more than the mass energy of the entire observable universe, making it impractical with our current understanding of physics. However, research into exotic forms of energy, such as negative energy or dark energy, might one day offer a way to make warp drives or other faster-than-light travel methods feasible. While interstellar travel remains a long-term goal, the prospect of humans living and working in space for extended periods is rapidly becoming a reality. The establishment of permanent space habitats, whether in orbit around Earth, on the Moon, or even on Mars, is one of the most exciting and challenging aspects of humanity's future in space. These habitats would need to be entirely self-sufficient, capable of recycling air, water, and waste, and providing food and energy for their inhabitants without relying on resupply missions from Earth. One promising concept for future space habitats is the idea of rotating space stations, which would generate artificial gravity through centrifugal force. In these stations, the structure would rotate around a central axis, and the rotation would create a force that mimics the effect of gravity, pulling people and objects toward the outer walls. This would allow humans to live and work in a more Earth-like environment, reducing the health risks associated with long-term exposure to microgravity, such as muscle atrophy and bone density loss. The concept of rotating space habitats has been around for decades, with designs like the O'Neill cylinder and the Stanford torus offering detailed visions of how such habitats could look and function. These large, rotating structures could house thousands of people, with living spaces, farms, factories, and research labs all contained within a self-sustaining ecosystem. On a smaller scale, lunar and Martian bases are likely to be the first permanent human outposts in space. NASA's Artemis program is already working on plans to establish a sustainable presence on the Moon, with missions to land astronauts on the lunar surface in the coming years. These bases would serve as a testing ground for technologies that could later be used on Mars, including life support systems, habitats, and techniques for extracting and utilizing local resources. For instance, water ice found in the Moon's shadowed craters could be harvested and converted into oxygen and hydrogen, providing breathable air and fuel for rockets. On Mars, the challenges are even greater due to the planet's thin atmosphere, low gravity, and high levels of radiation. However, plans for Mars colonies continue to advance, with companies like SpaceX leading the charge. SpaceX's Starship vehicle, currently under development, is designed to transport humans to Mars and beyond, with the long-term goal of establishing a self-sustaining colony on the Red Planet. Such a colony would need to rely heavily on in-situ resource utilization, ISRU, using Martian materials to build habitats, produce fuel, and grow food. Martian soil could potentially be used to create building materials, while underground water ice could provide a source of water for drinking and agriculture. Terraforming Mars, the process of altering its environment to make it more Earth-like, is a far more speculative idea, but one that has captured the imagination of scientists and futurists alike. The basic concept involves warming the planet and thickening its atmosphere so that liquid water could exist on the surface, and humans could potentially live without spacesuits. One proposed method of terraforming is to release greenhouse gases into the Martian atmosphere, trapping heat and gradually increasing the planet's temperature. Another idea is to use giant mirrors in space to reflect sunlight onto the poles, melting the ice caps and releasing carbon dioxide into the atmosphere. While these ideas remain in the realm of the theoretical, the dream of transforming Mars into a second Earth continues to inspire long-term thinking about humanity's future in space. Even as we explore the possibility of living on other planets, space stations closer to Earth may play a key role in humanity's expansion into space. Orbital space stations could serve as hubs for manufacturing, research, and even tourism. The International Space Station, ISS, has already demonstrated the value of such stations for scientific research, and as commercial spaceflight becomes more common, private space stations could follow. These stations might offer a range of services, from research and development in microgravity environments to space tourism experiences for private citizens. The rise of space tourism, led by companies like SpaceX, Blue Origin, and Virgin Galactic, is already transforming the way we think about access to space. In the coming decades, it's possible that space hotels and resorts could orbit the Earth, providing ordinary people with the opportunity to experience space travel firsthand. As we expand our presence in space, we will also need to consider how we manage and govern this new frontier. The Outer Space Treaty, signed in 1967, provides a framework for the peaceful use of space and prohibits the militarization of space or the establishment of national sovereignty over celestial bodies. However, as private companies and nations begin to explore the commercial potential of space, new legal and ethical questions are emerging. Who owns the resources on the Moon, Mars, or asteroids? How do we ensure that space exploration benefits all of humanity, rather than just a few wealthy individuals or corporations? These questions will need to be addressed as space exploration becomes a larger part of our global economy and society. The potential for conflict in space is also a growing concern. As more nations and companies launch satellites and spacecraft, space is becoming increasingly crowded, and the risk of collisions and interference is rising. Space debris, defunct satellites, rocket stages, and fragments from past collisions poses a serious threat to both crewed and uncrewed missions. Efforts to mitigate space debris and manage the growing population of objects in orbit will be critical to ensuring the safety and sustainability of space exploration. Despite these challenges, the future of space exploration holds immense promise. From the colonization of Mars to the search for life on distant exoplanets, the next century could see humanity take its place as a truly spacefaring civilization. The advances in technology, science, and exploration that we are witnessing today are just the beginning of a new era of discovery, one that will take us farther than we ever imagined possible. The universe is vast, and we have only just begun to scratch the surface of its wonders. With each new mission, each breakthrough in technology, and each step into the unknown, we are moving closer to a future where humanity's destiny lies among the stars. As humanity continues its ascent into the cosmos, one of the most profound transformations will be how we view our place in the universe. The era of space exploration has already reshaped our understanding of Earth and our relationship with the stars. But the coming decades promise to challenge our perceptions in ways that may be difficult to comprehend from today's perspective. From the technological revolutions needed for interstellar travel, to the potential for first contact with extraterrestrial life, and the ethical dilemmas of expanding human civilization beyond Earth, the future of space exploration holds the potential to redefine human existence. One of the most intriguing prospects in the near future is the ongoing search for alien life, specifically intelligent life. For years, the search for extraterrestrial intelligence, SETI, has scanned the skies for signals that might indicate the presence of advanced civilizations. While we have yet to detect such signals, the discovery of potentially habitable exoplanets has only intensified this search. As our telescopes and instruments become more powerful, scientists are optimistic that we may one day discover signs of life beyond Earth. The detection of a simple microbial organism on another planet would be a groundbreaking moment in human history, but discovering an advanced civilization would be nothing short of transformational. What would it mean if we found evidence of intelligent extraterrestrial life? The implications are vast and far-reaching. First and foremost, it would force us to reconsider the idea that Earth and humanity occupy a unique position in the universe. For centuries, humans have debated the possibility of life beyond Earth, but concrete evidence would raise profound questions about our own origins, the nature of intelligence, and the future of civilization. How would humanity react to the knowledge that we are not alone? Would it unite us, fostering a sense of solidarity as citizens of a greater cosmic community? Or would it spark fear, uncertainty, and even conflict as different cultures and nations grapple with the implications? Moreover, if we were to detect an alien civilization, the nature of their technology and communication would be a critical point of study. The distances between stars are so vast that any signal we receive would likely have traveled for thousands, if not millions, of years before reaching us. This means that the civilization that sent the signal could be long gone, or at a level of technological advancement that is far beyond anything we can imagine. Communication across such distances could be difficult, and we may not even recognize the form their messages take. Would they communicate with radio waves, laser pulses, or even gravitational waves? Or might they use a form of technology or communication that is completely alien to us? In the event of contact with an extraterrestrial civilization, one of the biggest challenges would be understanding their motivations. Are they explorers like us, seeking to learn about the universe? Or might they have more hostile intentions? While these questions remain speculative, they highlight the importance of preparing for the possibility of first contact. Some scientists and thinkers argue that we should be cautious about actively sending messages into space, fearing that broadcasting our presence could attract unwanted attention from advanced civilizations. Others believe that the potential benefits of making contact, such as gaining access to new technologies or learning from their experiences, outweigh the risks. As humanity continues to search for life beyond Earth, we are also turning our attention to the many other mysteries of the universe. One of the most profound of these is the origin of the universe itself. The Big Bang Theory, which describes how the universe began as a singularity and has been expanding ever since, is widely accepted by scientists. However, there are still many unanswered questions about what caused the Big Bang and what existed before it. Some theories suggest that our universe is just one of many in a multiverse, a vast collection of parallel universes, each with its own laws of physics and different outcomes for the evolution of life and matter. If true, the multiverse theory would revolutionize our understanding of reality, suggesting that our universe is just one small part of an unimaginably larger cosmos. In addition to exploring the origins of the universe, scientists are also probing its ultimate fate. Will the universe continue expanding forever, as predicted by the current understanding of dark energy, leading to a big freeze where all matter becomes dispersed and cold? Or could the expansion eventually reverse, resulting in a big crunch, where the universe collapses back into a singularity? Another possibility is the Big Rip, where the accelerating expansion of the universe becomes so extreme that it tears apart galaxies, stars, planets, and even atoms themselves. These scenarios offer a sobering reminder that the universe is not static, and that its future is still a matter of intense study and debate. At the same time, the study of black holes continues to push the boundaries of our knowledge of physics. Black holes are some of the most extreme and enigmatic objects in the universe, with gravitational forces so strong that not even light can escape. The recent success of the Event Horizon Telescope, which captured the first-ever image of a black hole, has opened up new avenues of research into these mysterious objects. Scientists are now investigating the possibility that black holes could act as gateways to other parts of the universe, or even to other dimensions. The idea of using black holes for interstellar travel, while still firmly in the realm of science fiction, is being explored by physicists studying the behavior of space-time under extreme conditions. One particularly fascinating aspect of black hole research is the concept of Hawking radiation, named after the renowned physicist Stephen Hawking. Hawking proposed that black holes are not completely black, but instead emit small amounts of radiation over time. This radiation causes black holes to slowly lose mass and eventually evaporate. While Hawking radiation has yet to be observed directly, the idea has profound implications for our understanding of black holes, suggesting that they are not eternal and may have a finite lifespan. Another area of cutting-edge research is the study of quantum mechanics and its implications for our understanding of reality. Quantum mechanics describes the behavior of particles on the smallest scales, where the classical laws of physics break down, and strange phenomena like superposition and entanglement occur. One of the most puzzling aspects of quantum mechanics is the role of the observer in determining the outcome of quantum events, a concept that has led to deep philosophical debates about the nature of reality. Some scientists believe that quantum mechanics could hold the key to solving some of the biggest mysteries in physics, such as the nature of dark matter and dark energy, or even the origins of the universe itself. The exploration of space is also raising ethical questions that humanity has never before faced. As we prepare to send humans to Mars and potentially other planets, we must grapple with the ethical implications of colonizing other worlds. Should we treat planets like Mars as we treated the Earth, using its resources to further human civilization? Or should we prioritize the protection of these environments, especially if we find evidence of life, however primitive? The idea of planetary protection has become a key consideration for space agencies like NASA and the European Space Agency, ESA, which are developing protocols to prevent the contamination of other planets with Earth-based microbes. The discovery of extraterrestrial life, even in microbial form, would raise profound ethical and philosophical questions. How should we interact with alien life forms? Should we study them or leave them undisturbed? What rights, if any, do they have? These questions are not just hypothetical. Missions to Mars, Europa, and Enceladus, where scientists believe life may exist beneath the surface, could bring us face to face with alien organisms in the near future. The decisions we make about how to handle these encounters will shape the future of space exploration and our relationship with the cosmos. As humanity extends its reach into space, the question of how we will govern our activities becomes increasingly important. Currently, space is considered a global commons, governed by international treaties like the Outer Space Treaty of 1967, which prohibits the militarization of space and the appropriation of celestial bodies by any one nation. However, as private companies and nations ramp up their efforts to explore and exploit space resources, new legal frameworks will be needed to address issues like property rights, resource extraction, and the management of space traffic. The establishment of lunar and Martian colonies, in particular, will raise complex questions about governance, sovereignty, and the distribution of wealth generated from space activities. At the same time, the commercialization of space is opening up new possibilities for economic growth and innovation. Companies like SpaceX, Blue Origin, and Virgin Galactic are leading the charge in the space tourism industry, while others are exploring the potential for asteroid mining, satellite-based internet services, and manufacturing in microgravity. The space economy is expected to grow significantly in the coming decades, with industries like energy production, telecommunications, and materials science benefiting from the unique conditions of space. As we stand on the threshold of a new era in space exploration, it is clear that the journey ahead will be filled with both challenges and opportunities. The exploration of space is not just about science and technology. It is about humanity's desire to push beyond the limits of the known and to seek out new frontiers. Whether we are searching for life on other planets, probing the mysteries of the universe, or building colonies on the Moon and Mars, space exploration represents the ultimate expression of human curiosity and ambition. The future is uncertain, but one thing is clear: the cosmos is vast, and we have only just begun to explore it. With each new discovery, we come closer to answering the fundamental questions that have driven humanity for millennia. Questions about our origins, our place in the universe, and the future of our species. As we continue this journey into the unknown, the stars are no longer distant and unreachable. They're the next step in humanity's quest to understand the cosmos and our place within it. The adventure of space exploration is just beginning, and the possibilities are truly limitless. As humanity's journey into space continues, the advancements in technology, exploration, and scientific understanding will transform not only how we see the universe, but also how we live and interact within it. One of the most profound impacts of space exploration will be the evolution of human civilization itself. The expansion into space, the development of new technologies, and the potential for encountering new forms of life will challenge us to rethink our social, political, and economic structures, as well as our fundamental values. The idea of becoming a multiplanetary species is not merely a technical challenge. It's a cultural and philosophical one, pushing us to redefine what it means to be human in a vast, interconnected cosmos. One of the key drivers of this transformation will be the rise of space colonies. As we move toward permanent settlements on the Moon, Mars, and beyond, the question of how these colonies will be governed, sustained, and integrated into the larger human community becomes increasingly important. The establishment of off-world colonies will not only provide new opportunities for exploration and scientific research, but also create new political entities, potentially independent or semi-autonomous from Earth. These colonies may develop their own cultures, social structures, and systems of governance, shaped by the unique challenges of living in space. For example, living on Mars or in orbit around distant planets will require new forms of cooperation and problem-solving. Unlike Earth, where resources like air, water, and food are abundant, if unevenly distributed, space colonies will need to create self-sustaining ecosystems where every drop of water and every breath of air is carefully managed. This will necessitate a high degree of collaboration and trust among colonists, as well as advanced technologies for recycling resources and maintaining life support systems. It's possible that space colonies will develop new forms of governance and social organization that emphasize resource efficiency, cooperation, and environmental stewardship, principles that could, in turn, influence life on Earth. The development of space colonies will also raise ethical questions about the ownership and use of space resources. As humans begin to mine the Moon, Mars, and asteroids for valuable materials, such as water, rare metals, and even helium-3, a potential fuel for nuclear fusion, we will need to establish rules and regulations to ensure that space resources are used responsibly and equitably. The question of who owns space and its resources is a complex one. Currently, international law, particularly the Outer Space Treaty, prohibits any nation from claiming sovereignty over celestial bodies, but it is less clear about the rights of private companies to exploit space resources. As the space economy grows, there will be increasing pressure to develop legal frameworks that balance the interests of nations, corporations, and the common good of humanity. In addition to the economic and political challenges, the expansion into space will also have profound cultural implications. Space has always been a source of wonder and inspiration, and as we begin to live and work in space, it will undoubtedly influence art, literature, philosophy, and spirituality. How will our understanding of concepts like home, community, and identity change when humans are living on multiple planets? Will new forms of art and expression emerge, inspired by the experience of weightlessness, the vastness of space, or the alien landscapes of other worlds? Space exploration may also lead to new spiritual and philosophical movements, as humanity grapples with the existential questions raised by our place in the universe. Just as the discovery of the New World during the Age of Exploration led to a cultural renaissance in Europe, so too might the exploration of space spark a new wave of creativity and intellectual growth. At the same time, the expansion of human presence in space will raise important ethical considerations about how we interact with the environments we encounter. The concept of planetary protection, ensuring that we do not contaminate other planets or moons with Earth-based organisms, will become even more critical as we explore worlds like Mars, Europa, and Enceladus, which may harbor life. If we discover life on another planet, even in microbial form, how should we treat it? Do we have a moral obligation to protect alien ecosystems, or should we prioritize human exploration and settlement? These questions are not only scientific but deeply ethical, and they will require careful consideration as we expand our footprint in the cosmos. Another profound impact of space exploration will be the development of new technologies that can improve life on Earth. Many of the innovations needed for space travel, such as advanced robotics, artificial intelligence, renewable energy, and sustainable agriculture, will have direct applications on Earth, particularly in addressing global challenges like climate change, resource scarcity, and economic inequality. For example, the technologies developed to grow food in space, such as hydroponics, vertical farming, and genetically engineered crops, could revolutionize agriculture on Earth, helping to feed a growing global population while reducing the environmental impact of farming. Similarly, the development of renewable energy technologies for space exploration, such as solar power and fusion energy, could provide new sources of clean energy for Earth. Space-based solar power, where satellites in orbit collect solar energy and beam it down to Earth, has the potential to provide abundant, renewable energy without the need for fossil fuels. Additionally, the discovery of helium-3 on the Moon, a rare isotope that could be used as fuel for nuclear fusion, could provide a nearly limitless source of clean energy if we can develop the technology to harness it. These innovations have the potential to not only sustain life in space, but also address some of the most pressing challenges facing humanity on Earth. One of the most exciting developments in the future of space exploration is the possibility of terraforming, altering the environment of a planet to make it more Earth-like and habitable for humans. While this idea has been popularized in science fiction, scientists are beginning to seriously explore the possibility of terraforming Mars. The basic idea is to increase the planet's temperature and thicken its atmosphere, allowing liquid water to exist on the surface and potentially supporting human life. One proposed method of terraforming Mars is to release greenhouse gases into the atmosphere, trapping heat and warming the planet over time. Another idea is to use giant mirrors in space to reflect sunlight onto Mars poles, melting the ice caps and releasing carbon dioxide into the atmosphere. While terraforming Mars would be an enormous technical challenge, it could one day allow humans to transform an inhospitable world into a new home. Terraforming raises important ethical and environmental questions. Should we alter the environment of another planet, even if it is currently barren and lifeless? What are the potential consequences of such actions, not only for the planet itself, but for the future of space exploration? Some scientists argue that we should focus on protecting and preserving the natural state of planets and moons, particularly if they may harbor life, rather than attempting to reshape them to suit human needs. Others believe that terraforming is a necessary step in ensuring the long-term survival of humanity, particularly in the face of potential threats to Earth, such as climate change, asteroid impacts, or nuclear war. As we move closer to making these possibilities a reality, these debates will become increasingly important. The idea of humanity spreading out across the stars also raises philosophical questions about our place in the universe. What will it mean to be human when we are no longer confined to a single planet? How will our sense of identity, culture, and society evolve as we establish colonies on distant worlds and interact with alien environments? These are questions that go beyond science and technology, touching on the very essence of what it means to be human. At the same time, the development of space exploration will likely lead to new forms of international collaboration and competition. Space has traditionally been a domain of international cooperation, with projects like the International Space Station, ISS, bringing together scientists and engineers from different nations to work toward common goals. However, as space becomes more accessible and valuable, it may also become a source of geopolitical tension. The race to establish a permanent presence on the Moon or Mars, the competition for valuable space resources, and the militarization of space are all potential flashpoints in the future of space exploration. To avoid conflict and ensure that space remains a domain of peace and exploration, new international agreements and governance structures will likely be needed. These agreements will need to address questions of resource ownership, environmental protection, and the rights of spacefaring nations and companies. They will also need to ensure that the benefits of space exploration are shared equitably among all of humanity, not just the wealthy or technologically advanced nations. Looking further ahead, the idea of human interstellar travel, traveling to other star systems, remains one of the most exciting but challenging goals for the future. While the distances between stars are immense and the technology required is far beyond our current capabilities, the dream of exploring other star systems is one that continues to inspire scientists and futurists alike. Concepts like generation ships, where humans would live and reproduce over many generations on a spacecraft traveling between stars, or advanced propulsion systems like nuclear fusion or antimatter engines, offer tantalizing glimpses of how interstellar travel might one day become possible. Even more speculative is the idea of using wormholes or warp drives to travel faster than the speed of light, allowing humans to reach distant star systems in a matter of days or weeks rather than centuries. While these ideas remain firmly in the realm of theoretical physics, ongoing research into the nature of spacetime, quantum mechanics, and the fundamental forces of the universe may one day provide the key to unlocking the possibility of faster-than-light travel. As we look to the future, it's clear that space exploration holds the potential to transform not only our understanding of the universe, but also the very fabric of human society. The challenges we face in space, whether technical, ethical, or philosophical, will require new ways of thinking, new forms of collaboration, and new visions for the future. But with each step we take into the cosmos, we come closer to realizing the dream of becoming a truly spacefaring civilization. The stars await, and the future of humanity is brighter than ever, filled with endless possibilities for discovery, innovation, and exploration. As humanity's exploration of space continues to evolve, one of the most transformative developments on the horizon is the convergence of space exploration and artificial intelligence, AI. AI will become an essential component in future space missions, not only enhancing the capabilities of robotic explorers, but also assisting humans in making decisions, navigating the challenges of deep space, and sustaining long-term colonies on other planets. The synergy between AI and space exploration is already evident in the current generation of rovers, satellites, and autonomous spacecraft, but the role of AI will become even more profound as missions grow more complex and distant. One of the most immediate uses of AI in space exploration is in the realm of autonomous operations. Today's Mars rovers, like Perseverance and Curiosity, are equipped with AI systems that allow them to navigate the Martian surface, avoid obstacles, and make decisions about which samples to collect, all with minimal input from Earth-based controllers. Given the long communication delays between Earth and Mars, up to 24 minutes one way, AI is essential for enabling these rovers to operate semi-independently. As we push further into space, AI will become even more critical. For instance, on missions to the outer planets or interstellar space, communication delays will be even greater, making real-time human control impossible. Spacecraft will need to be fully autonomous, able to perform scientific research, respond to emergencies, and even repair themselves without human intervention. In addition to improving robotic exploration, AI will play a crucial role in supporting human space missions. On the International Space Station, ISS, AI systems like Simon, Crew Interactive Mobile Companion, are already being tested to assist astronauts with tasks such as running experiments, managing schedules, and troubleshooting technical issues. As missions to the Moon, Mars, and beyond become a reality, AI assistants will become indispensable for helping astronauts manage the complexities of life in space. These AI systems will act as companions, technicians, and researchers, providing real-time data analysis, monitoring the health of both the crew and the spacecraft, and even offering psychological support during long missions in the isolated and confined environments of space habitats. The role of AI will extend far beyond assisting astronauts with everyday tasks. In the context of long-duration space travel, such as a mission to Mars, AI will be responsible for managing life support systems, energy consumption, and the delicate balance of resources needed to sustain human life. For example, in a Martian habitat, AI systems will monitor oxygen levels, water filtration, waste recycling, and food production, ensuring that the colony can remain self-sufficient. The precision and speed of AI in analyzing data and adjusting systems in real time will be crucial in preventing crises and ensuring the survival of the crew. As we move toward the goal of establishing permanent colonies on the Moon and Mars, AI's ability to manage complex systems will be tested in new and unprecedented ways. Lunar or Martian colonies will be entirely dependent on their life support infrastructure, and the margin for error will be slim. AI systems will need to be robust, adaptable, and capable of operating autonomously for extended periods, particularly in situations where human intervention is delayed or impossible. These systems will also need to be resilient to the harsh environments of space, capable of repairing themselves or improvising solutions to unforeseen challenges. AI will also play a critical role in the construction of space habitats. On the Moon or Mars, building permanent settlements will require the use of local resources, a process known as in situ resource utilization, ISRU. Autonomous robots equipped with AI will be tasked with mining lunar or Martian soil, extracting water from ice deposits, and even 3D printing habitats using regolith. These robots will need to work in coordination with one another, much like a colony of ants, to construct the infrastructure necessary for human habitation. By using AI to automate construction and resource extraction, we can reduce the cost and risk of sending humans into space to do these labor-intensive and potentially dangerous tasks. The potential of AI extends even further when we consider the exploration of deep space. In the quest to study distant exoplanets or phenomena like black holes and dark matter, AI will be indispensable in processing the vast amounts of data collected by space telescopes and other instruments. Missions like the James Webb Space Telescope (JWST) are already producing huge quantities of data, far more than can be analyzed manually. AI algorithms, particularly those using machine learning, can sift through this data to identify patterns, detect anomalies, and make discoveries that might otherwise be missed. For example, AI has already been used to discover new exoplanets by analyzing data from the Kepler Space Telescope, identifying subtle changes in the light from distant stars that indicate the presence of planets. As AI becomes more sophisticated, it may even be able to develop new hypotheses and theories about the universe, pushing the boundaries of human knowledge. AI systems could be trained to recognize patterns in the data that are too complex or subtle for humans to detect, uncovering new insights into the nature of dark matter, dark energy, or the behavior of black holes. These AI-driven discoveries could revolutionize our understanding of the universe, leading to breakthroughs that would have been impossible to achieve using traditional methods of analysis. The future of space exploration will also see AI playing a key role in the development of advanced propulsion systems. Concepts like nuclear fusion propulsion, antimatter engines, and even theoretical warp drives are extremely complex, requiring precise control over vast amounts of energy. AI systems could manage these propulsion systems, optimizing them for efficiency and safety while minimizing the risk of failure during long-duration space travel. In the case of interstellar missions, where travel times are measured in decades or even centuries, AI will be essential for maintaining the spacecraft, adjusting its course, and ensuring that it reaches its destination safely. One of the most exciting possibilities for AI in space exploration is the development of self-replicating robots or autonomous spacecraft that can build and maintain themselves. These machines could be sent to distant star systems or asteroids, where they would mine local resources to create new versions of themselves, expanding the reach of human exploration without the need for constant resupply from Earth. This concept, known as von Neumann probes, could enable the rapid exploration of vast areas of space, providing data and insights from places that would otherwise be unreachable for human missions. In addition to enhancing space exploration, AI will fundamentally reshape the way humans interact with space environments. As we establish permanent colonies on the Moon, Mars, or other planets, AI systems will be integrated into every aspect of life in these environments. From controlling the climate inside habitats to managing transportation systems, AI will be the backbone of space society, allowing humans to focus on scientific research, innovation, and the exploration of new frontiers. However, the increasing role of AI in space exploration also raises important ethical questions. As we delegate more decision-making power to AI systems, we must ensure that these systems are designed with robust ethical frameworks. How do we ensure that AI systems make decisions that prioritize the safety and well-being of astronauts and space colonists? How do we prevent AI from making catastrophic errors in life support systems, navigation, or resource management? These are questions that will need to be addressed as AI becomes an integral part of our spacefaring future. Moreover, as AI systems become more autonomous and capable, we will need to consider the implications of their actions in the broader context of space exploration. For instance, if AI-driven spacecraft discover life on another planet, how should they interact with that life? What ethical guidelines should govern the exploration and exploitation of alien ecosystems? As we venture further into the cosmos, these ethical questions will become increasingly relevant, shaping the future of space exploration and our relationship with the universe. AI will also play a crucial role in the search for extraterrestrial intelligence (SETI). Current SETI efforts rely on the analysis of radio signals from distant stars, but as AI algorithms become more sophisticated, they will be able to analyze vast amounts of data more quickly and efficiently, increasing the chances of detecting a signal from an alien civilization. AI could even be used to communicate with extraterrestrial intelligences, interpreting signals and responding in ways that human language and logic may not be capable of. The development of AI will also revolutionize space medicine, helping astronauts manage the physical and psychological challenges of long-duration space travel. AI systems could monitor the health of astronauts in real time, detecting signs of illness or injury before they become serious, and even performing surgical procedures if necessary. AI could also assist in the development of personalized medical treatments, optimizing healthcare for individuals based on their unique biology and the stresses of space environments. Looking further into the future, the convergence of AI and space exploration may lead to even more radical developments, such as the merging of human and machine intelligence. Some futurists envision a future where astronauts or space colonists are augmented with AI implants, enhancing their cognitive abilities and allowing them to interface directly with spacecraft, habitats, and other systems. This fusion of human and AI intelligence could enable humans to adapt more easily to the challenges of space exploration, allowing us to explore more distant and inhospitable environments. Ultimately, the integration of AI into space exploration represents a new frontier in humanity's relationship with technology. As AI systems become more capable, they will not only assist us in exploring the universe, but also help us understand our place within it. AI will be the key to unlocking the full potential of space exploration, enabling us to push beyond the boundaries of what is currently possible and reach for the stars in ways that were once unimaginable. The future of space is intertwined with the future of AI, and together, they will shape the next chapter of human evolution as we move from being a planetary species to a truly cosmic one. As humanity continues to intertwine its fate with space exploration and artificial intelligence, the boundaries between what we consider science fiction and scientific reality will continue to blur. The future of space exploration isn't just about reaching distant planets or uncovering the mysteries of the universe. It's also about transforming the human species, our society, and our very understanding of life and intelligence. In this next stage of our evolution, we are likely to see an unprecedented convergence of technologies, cultures, and ideas that will redefine humanity's place in the cosmos. One of the most transformative ideas on the horizon is the concept of cybernetic enhancement and human augmentation. As space exploration pushes the limits of human endurance and adaptability, integrating advanced technology directly into the human body may become necessary to survive and thrive in hostile environments. The long-term exposure to microgravity, radiation, and isolation in deep space presents significant health risks to astronauts, but by merging biology with technology, we may be able to overcome these challenges. Augmented humans, those with embedded AI, robotic limbs, or enhanced cognitive abilities, could become a new norm for spacefarers, enabling us to adapt to the unique demands of extraterrestrial life. For instance, cybernetic limbs or exoskeletons could help astronauts maintain their physical strength and mobility in low-gravity environments like the Moon or Mars, where traditional human physiology might struggle. Advanced AI implants could enhance astronauts' ability to process complex information quickly, allowing them to monitor life support systems, perform repairs, and make critical decisions without relying on constant communication with Earth. Augmented vision, hearing, or even new senses designed specifically for space environments could be developed, allowing humans to perceive radiation levels, detect subtle changes in gravity, or even navigate in the absence of familiar Earth-based sensory cues. The integration of biotechnology and genetic engineering will also play a crucial role in shaping the future of space exploration. As we venture deeper into space and confront extreme conditions on other planets, it may become necessary to modify the human genome to improve resilience against radiation, extreme temperatures, or low-gravity environments. Gene editing technologies like CRISPR could allow us to enhance human DNA to repair damage caused by cosmic radiation, or to adapt our biology to thrive in environments with lower oxygen levels or higher levels of carbon dioxide, like those found on Mars. While these ideas raise significant ethical questions, they also offer a glimpse of how humanity might evolve to become a truly spacefaring species. In parallel with human augmentation, artificial life forms and synthetic biology will become key tools in the future of space colonization. Scientists are already exploring ways to engineer organisms that can thrive in the harsh conditions of space or on other planets. For example, microorganisms could be genetically modified to survive in Martian soil, where they could be used to produce oxygen, break down toxic compounds, or even assist in growing food. Algae and bacteria, which can be engineered to produce vital resources like oxygen, water, and food, may play a central role in the sustainability of space colonies, creating closed-loop ecosystems that require minimal input from Earth. Terraforming, the process of altering an alien planet's environment to make it more Earth-like, could one day be enhanced by synthetic biology. Genetically engineered organisms could be introduced to planets like Mars to initiate processes that generate a thicker atmosphere or transform the soil to support plant life. This gradual, bio-driven form of terraforming would allow humans to reshape alien worlds over centuries or millennia, making them suitable for long-term human habitation. As these technological advancements unfold, the ethical and philosophical questions surrounding space exploration will only grow more complex. Human enhancement, gene editing, and synthetic biology bring with them concerns about identity, equity, and the definition of life itself. If we begin modifying human DNA to adapt to space, what does it mean to be human? Will space colonists who have been genetically engineered to survive in alien environments still see themselves as Earthlings? Or will new identities and cultures emerge, shaped by their unique adaptations and experiences? Moreover, the expansion of human presence into space raises significant questions about our responsibility to the ecosystems we encounter. Should we prioritize the protection of pristine alien environments, or is it acceptable to alter them to suit human needs? If we discover microbial life on Mars, Europa, or Titan, what rights do these organisms have, and how should we interact with them? The idea of planetary protection, which currently focuses on preventing contamination of other planets by Earth-based life, will need to evolve as we consider the broader ethical implications of altering or exploiting alien ecosystems. Another profound question relates to the potential discovery of intelligent extraterrestrial civilizations. While we have not yet found definitive evidence of such civilizations, the discovery of exoplanets in the habitable zones of distant stars continues to fuel speculation about the existence of alien life. If we were to detect a signal from an advanced alien civilization, how would humanity respond? The SETI, Search for Extraterrestrial Intelligence, program has long been scanning the skies for such signals, but the implications of making contact are still the subject of intense debate. Will we try to communicate with these extraterrestrial beings? What form might such communication take? Given the vast distances between stars, it's likely that any signals we receive would be thousands of years old, meaning that the civilization that sent them could be long gone. If we do manage to establish contact, we may find that alien languages, thought processes, or even forms of communication are so different from our own that meaningful dialogue is incredibly difficult, or perhaps impossible. Moreover, how would contact with an alien civilization impact human society, religion, politics, and culture? The realization that we are not alone in the universe would likely lead to a profound shift in how we see ourselves and our place in the cosmos. While the search for extraterrestrial life is an exciting and speculative endeavor, one of the most immediate impacts of space exploration will be on Earth itself. Space-based technologies are already transforming industries ranging from telecommunications to agriculture, and the expansion of space activities will bring even more opportunities for economic growth and innovation. Satellite networks, like Starlink, are poised to revolutionize global internet access, providing high-speed, low-latency connections to remote areas that have historically been underserved. These networks could help bridge the digital divide, enabling people in developing regions to access education, healthcare, and economic opportunities. Space mining, the extraction of valuable resources from asteroids or the moon, also promises to reshape the global economy. Asteroids are rich in metals like platinum, gold, and rare earth elements, which are critical for the production of electronics, renewable energy technologies, and other advanced industries. Mining these resources in space could provide a virtually limitless supply of materials, reducing the need for environmentally destructive mining practices on Earth. However, the rise of space mining also raises questions about ownership, governance, and the equitable distribution of resources. Who owns the resources in space, and how should they be shared among nations and companies? These questions will become increasingly urgent as space-based industries expand. Energy production is another area where space technologies could have a profound impact. Space-based solar power, where solar panels in orbit collect energy from the sun and beam it down to Earth, has the potential to provide abundant, clean energy without the limitations of weather, daylight hours, or geographic constraints. While the technology to make space-based solar power economically viable is still in development, it represents one of the most promising solutions to the global energy crisis. Moreover, the development of nuclear fusion, which could be fueled by helium-3 harvested from the moon, could provide humanity with a nearly limitless source of clean energy. As space becomes an increasingly important part of the global economy, new governance structures will be needed to manage space traffic, resource rights, and environmental protection. Current international treaties, like the Outer Space Treaty, provide a foundation for the peaceful use of space, but they will need to be updated to address the complexities of space commerce, tourism, and colonization. Space is currently a global commons, but as nations and private companies begin to stake claims on the moon, Mars, and asteroids, questions about sovereignty, property rights, and environmental stewardship will become more pressing. The future of space exploration will also see a growing emphasis on international collaboration. While space has historically been a domain of competition, particularly during the Cold War, the complexities and costs of modern space exploration will require nations to work together. International partnerships, like those that created the International Space Station, will be essential for tackling the massive technical, financial, and logistical challenges of establishing colonies on the Moon or Mars. Space exploration could become a unifying force, bringing nations together in the shared pursuit of knowledge and discovery. However, the potential for geopolitical tensions in space cannot be ignored. As space becomes more commercialized and militarized, there is a risk that competition for resources, territory, or strategic advantage could lead to conflict. The militarization of space, particularly the development of anti-satellite weapons and space-based defense systems, poses a significant threat to global security. Ensuring that space remains a domain of peaceful exploration and cooperation will require strong international agreements and mechanisms for conflict resolution. In the end, space exploration represents both a technological challenge and a philosophical journey. As we push the boundaries of what is possible, we are also pushing the boundaries of what it means to be human. The stars beckon, and as we reach for them, we are forced to confront fundamental questions about life, intelligence, and our place in the universe. The future of space is not just about science or technology. It is about the evolution of human civilization, the discovery of new worlds, and the expansion of our collective imagination. The cosmos is vast, and our journey into it has only just begun. As we look to the future of space exploration and humanity's role within the cosmos, we begin to realize that our expansion into the stars will not simply be about scientific discoveries or technological achievements. It will fundamentally reshape our sense of identity, challenge our social structures, and confront us with ethical dilemmas that will redefine how we view life, consciousness, and our responsibility as stewards of both Earth and the wider universe. One of the most important aspects of this journey will be the cultural evolution that accompanies space colonization. Human society has always been shaped by its environment, and the extreme conditions of space, the Moon, Mars, and potentially even exoplanets will force us to adapt in ways we can hardly anticipate. Each colony, whether it is on a space station, a lunar base, or a Martian settlement, will have its own unique challenges, opportunities, and constraints, leading to the development of new customs, traditions, and forms of social organization. In the context of space habitats, whether they be on the Moon, Mars, or massive rotating space stations, *** culture and community *** will evolve differently than anything we've seen on Earth. The isolation of space, the dependence on technology for survival, and the psychological pressures of living in enclosed environments far from home will foster new forms of social cohesion. Colonies will need to create a sense of identity and purpose that goes beyond survival, encouraging art, music, literature, and other cultural expressions to thrive. Over time, these space communities might even develop entirely new forms of cultural identity, distinct from those on Earth, shaped by the unique challenges and rhythms of life beyond our planet. For example, space colonies might adopt new systems of time. Martian colonists, for instance, will have to contend with a day that is slightly longer than Earth's, 24 hours and 39 minutes, and a year that is almost twice as long. This could lead to the development of a new calendar system or altered work-life rhythms that accommodate the Martian day. Similarly, lunar colonies might operate on a cycle that accounts for the moon's slow rotation, with days and nights each lasting about 2 Earth weeks. These differences in timekeeping could shape everything from daily routines to long-term planning and could foster a cultural divide between Earth and its colonies, where the passage of time itself is experienced differently. Education in space will also take on new dimensions. With colonies potentially light years away from Earth, education systems will need to be more self-sufficient and adapted to the unique challenges of space life. Children born and raised in space might have vastly different learning experiences than those on Earth, with an emphasis on survival skills, engineering, robotics, and environmental management. There will also be new fields of study related to space exploration, from planetary geology to extraterrestrial ecology, that will help future generations better understand and interact with their surroundings. Religion and spirituality will likely evolve as well, influenced by humanity's new position within the cosmos. The experience of gazing upon Earth from space, a fragile blue marble suspended in the blackness of the universe, has been described by astronauts as a deeply spiritual moment, often referred to as the overview effect. As humans venture deeper into space, encountering new worlds and possibly even alien life, our religious and philosophical traditions will be challenged and transformed. New space-based spiritual movements might emerge, reflecting the profound sense of awe and mystery that comes with living among the stars. Religious rituals and beliefs could be adapted to fit the realities of space life, where traditional practices might need to be modified to accommodate microgravity or life in enclosed habitats. Another major cultural shift will be driven by the expansion of the space economy. As we extract resources from asteroids, establish space tourism industries, and develop commercial enterprises in orbit and beyond, the economic landscape of humanity will change dramatically. The rise of space capitalism, where private companies play a central role in exploring and developing the cosmos, will raise questions about wealth distribution, resource ownership, and economic justice. Just as the Industrial Revolution reshaped society on Earth, the commercialization of space will create new opportunities and challenges, potentially leading to both unprecedented wealth and deep inequalities. One of the most significant developments will be the establishment of space-based economies that are less reliant on Earth. Over time, as colonies become more self-sufficient, they may develop their own economic systems, trading resources, goods, and services with Earth and with other space settlements. This could lead to the creation of new currencies, new financial markets, and even new forms of economic governance that are tailored to the realities of space life. The development of space-based industries, such as asteroid mining, space manufacturing, and zero-gravity research, will further drive economic growth. But they will also require careful management to ensure that the benefits of space exploration are shared equitably across humanity. However, the development of a space economy also comes with the risk of exploitation and environmental degradation. Just as humans have overexploited Earth's resources, there is the danger that we could repeat these mistakes in space, overmining asteroids or destroying the fragile environments of other planets in the pursuit of profit. The challenge will be to develop a sustainable approach to space exploration that balances the needs of economic development with the protection of extraterrestrial ecosystems. This will require new regulatory frameworks, ethical guidelines, and international agreements to ensure that space remains a shared resource, rather than a battleground for competing corporate interests. The expansion into space will also force us to rethink issues of law and governance. Currently, space law is governed by a patchwork of international treaties, most notably the Outer Space Treaty of 1967, which establishes space as the province of all mankind and prohibits claims of sovereignty over celestial bodies. However, as space exploration becomes more commercialized and as private companies and nations begin to stake claims on lunar and Martian resources, these legal frameworks will need to be expanded and updated. How will we govern Mars, for instance? Will Martian colonies be governed by Earth-based authorities, or will they eventually declare independence, forming their own governments and legal systems? The idea of space citizenship could also emerge. As people are born and raised in space, will they identify primarily as citizens of Earth, Or will they adopt new identities as citizens of space colonies? Space settlements could develop their own political systems, with constitutions, laws, and governance structures that reflect the unique needs and values of their populations. These space-based governments may operate more as direct democracies, where citizens vote on important issues in real time, or they may experiment with entirely new forms of governance that are better suited to the challenges of life in space. The question of human rights in space will also become critical. As we develop space colonies, how do we ensure that the rights and freedoms of all space settlers are protected? What are the rights of space colonists to self-governance, resource ownership, or environmental protection? These questions will become even more urgent if space colonies are established by private companies, raising concerns about corporate governance and the potential for exploitation. Ensuring that space is governed in a way that promotes equality, fairness, and sustainability will be one of the most important challenges of the next century. The ethical implications of space colonization go beyond issues of governance and economics. As we venture into space, we will need to grapple with questions about our impact on other worlds. Should we terraform Mars or other planets to make them more habitable for humans, even if it means potentially destroying native ecosystems? What ethical responsibilities do we have to protect alien life forms, even if they are microscopic or non-intelligent? The discovery of extraterrestrial life, whether microbial or intelligent, would force us to rethink our relationship with the universe and our role as stewards of life beyond Earth. The search for alien life, in particular, could lead to one of the most profound shifts in human consciousness. For decades, the SETI program has been scanning the skies for signals from extraterrestrial civilizations. But if we were to detect such a signal, it would raise existential questions about humanity's place in the universe. How would we communicate with an alien species? Would they share our values? Or would their motivations be incomprehensible to us? Would contact with an alien civilization lead to a new era of cooperation and discovery? Or would it provoke fear and conflict? In the absence of contact with extraterrestrial civilizations, the idea of post-humanity, the evolution of humans into entirely new forms of life, may emerge as one of the dominant narratives of the space age. As we develop technologies like AI, gene editing, and cybernetic enhancement, humans may begin to transcend the biological limits that have constrained us for millennia. Future generations of spacefarers might not resemble us at all, evolving into new species adapted to the unique environments of space. In 1,000 years, the descendants of today's astronauts might be genetically engineered to withstand radiation, possess enhanced cognitive abilities, or even merge with AI to form a new type of consciousness. The idea of human-AI hybrids, where biological and artificial intelligence are seamlessly integrated, offers a glimpse into a future where the distinction between human and machine becomes increasingly blurred. These hybrids could be essential for long-duration space travel, allowing humans to survive the immense challenges of interstellar exploration. By augmenting our brains with AI, we could enhance our ability to process information, solve complex problems, and even transcend the limitations of our physical bodies. This blending of human and machine intelligence might lead to new forms of consciousness, where individuals exist as both biological beings and digital entities, capable of inhabiting virtual environments or exploring the cosmos as non-physical entities. In the distant future, the ultimate form of space exploration may involve mind uploading, the transfer of human consciousness into digital form. In this scenario, humans would no longer need physical bodies to explore the cosmos. Instead, we could upload our minds into spacecraft or robotic avatars, traveling vast distances across the universe without the limitations of biological life. This form of exploration would open up entirely new possibilities for interacting with alien worlds, allowing us to experience different environments and realities without the constraints of our physical form. As we contemplate these future possibilities, it is clear that the expansion of humanity into space is not just a scientific or technological endeavor. It is a philosophical and existential journey. The decisions we make in the coming decades will shape the future of humanity, our relationship with the cosmos, and the very nature of life itself. The stars await us, and with them come questions that will challenge everything we think we know about ourselves, our planet, and our place in the universe. The future is vast, and as we venture into the unknown, we are only beginning to scratch the surface of what is possible. The next chapter of human evolution will be written among the stars, and it promises to be more extraordinary than we can currently imagine. As humanity progresses into the vast expanse of space, the questions we face grow in complexity, ambition, and consequence. The next phase of our cosmic journey will not only test our scientific and engineering prowess, but also challenge the very core of our ethical frameworks, cultural norms, and existential understandings. With space exploration moving beyond the realm of government agencies and into the hands of private enterprises and international collaborations, the future promises a diverse set of challenges and opportunities. The adventure ahead is as much about adapting to life in space as it is about transforming our societies, our bodies, and even our understanding of reality. The next great leap, living permanently in space. One of the most significant milestones in humanity's expansion into space will be the establishment of permanent human settlements beyond Earth. While temporary missions to the Moon or Mars are expected in the near future, the goal of creating self-sustaining colonies that can function indefinitely without constant resupply from Earth represents an entirely new level of complexity. These space habitats will need to be designed to accommodate not just the physical needs of their inhabitants, such as food, water, air, and shelter, but also their psychological and social needs. Research from the International Space Station, ISS, has already shown that long-term exposure to space environments poses significant challenges to human health, including muscle atrophy, bone density loss, and exposure to harmful cosmic radiation. However, even more pressing is the need to address the mental health and social well-being of those living in isolated, confined environments for extended periods. The challenge of designing space habitats will require interdisciplinary collaboration between architects, engineers, psychologists, and sociologists to ensure that these environments are not only functional, but also livable. Habitats must foster a sense of community and belonging, combating the loneliness and psychological stress that may accompany life far from Earth. Advances in virtual reality, VR, and augmented reality, AR, could help mitigate the sense of isolation by allowing space colonists to immerse themselves in virtual environments that simulate natural landscapes or even connect with family and friends on Earth in real time, despite the vast distances. Space cities and sustainable ecosystems. Looking even further into the future, the creation of space cities, large-scale, permanent habitats that house thousands or even millions of people, will represent one of the most ambitious undertakings in human history. These space cities could exist on the Moon, Mars, or even in orbit around other planets. Some visions of these cities include massive rotating space stations that generate artificial gravity through centrifugal force, allowing humans to live in environments that mimic Earth's gravity while floating in the vacuum of space. These cities will rely on the development of closed-loop ecosystems, where resources are continuously recycled and reused. Water, for instance, would be filtered and purified, circulating through the city in a closed system, while waste materials would be composted or processed for reuse as fertilizers or building materials. Food production will also need to be self-sustaining, with space farms growing crops in hydroponic or aeroponic systems that require minimal water and soil. These systems could be integrated into the architecture of space cities, with vertical farms and green spaces serving both practical and psychological purposes, providing food while also offering colonists a connection to nature. The idea of terraforming, transforming the surface and atmosphere of a planet like Mars to make it more Earth-like, continues to be a subject of intense speculation. While we are likely centuries away from having the technology to fully terraform a planet, smaller-scale terraforming efforts could be explored in the relatively near future. These might include using artificial means to warm specific regions of Mars, or creating enclosed biodomes where Earth-like ecosystems could flourish. Whether or not we should terraform Mars, given the potential ethical concerns about altering an alien environment, will remain a central debate as we advance in space exploration. The evolution of law and governance in space. As humans establish colonies beyond Earth, the question of governance will become increasingly important. Who will govern space settlements, and how will laws be enforced in these distant colonies? Will colonies on Mars or the Moon operate under the jurisdiction of Earth-based governments, Or will they develop their own independent systems of governance? The establishment of new legal and political systems in space will likely mirror the history of human expansion on Earth, but with added complexities. For now, the legal framework for space is based on international treaties such as the Outer Space Treaty of 1967, which declares space a global commons and prohibits claims of sovereignty over celestial bodies. However, as space exploration becomes more commercialized, and as private companies begin to extract resources from asteroids or the moon, new legal frameworks will be needed. These laws must address issues of property rights, resource ownership, and the protection of extraterrestrial environments. One possibility is that space colonies could operate as democratic federations, with each colony governing itself, but remaining loosely connected to Earth through international agreements. Alternatively, space governance might evolve into entirely new political forms. Direct democracies where decisions are made collectively by colonists through real-time digital voting, or even AI-assisted governments where advanced algorithms help manage resources, laws, and public welfare. The emergence of space law will not only address issues of governance within colonies but also between Earth and space. As humanity ventures beyond its home planet, the potential for conflicts over resources, territory, and trade could arise. How will disputes between Earth-based corporations and space-based colonies be settled? What happens if two different colonies claim the same asteroid for mining purposes? The development of a robust legal system for space is essential to ensure that humanity's expansion into space remains peaceful, equitable, and sustainable. Ethics of space colonization and alien ecosystems. The ethical challenges of space exploration will only grow as humans venture further into the cosmos. The discovery of alien life, whether microbial or intelligent, would fundamentally alter our understanding of life in the universe and raise profound ethical questions. If we discover microbial life on Mars or in the oceans beneath Europa's icy surface, how should we interact with it? Do we have a moral obligation to protect alien ecosystems, even if they are non-intelligent? Or should human needs take precedence? The question of planetary protection will become even more pressing as we begin to establish permanent settlements on other worlds. Currently, space agencies adhere to strict guidelines to avoid contaminating other planets with Earth-based microbes, but these guidelines will be tested as we begin to terraform planets or mine their resources. As space colonies expand, the potential for irreversible changes to the environments of other planets grows, raising questions about humanity's responsibility as stewards of the cosmos. The philosophical implications of post-humanity. Perhaps one of the most profound consequences of humanity's expansion into space is the possibility of post-human evolution. As humans spend generations living in space or on other planets, they may undergo significant biological, psychological, and cultural transformations. Life in microgravity, exposure to cosmic radiation, and the isolation of space could lead to evolutionary changes over time, creating new forms of human life that are better adapted to these environments. Genetic engineering could accelerate this process. Humans might be genetically modified to withstand radiation, adapt to low-gravity environments, or even breathe different atmospheres. As space colonists adapt to their new environments, they may begin to diverge from Earth-based humans, leading to the emergence of new species. Over millennia, the descendants of today's spacefarers might look very different from the humans who remain on Earth. These changes may not be limited to biology. As humans integrate AI into their bodies and minds, we could see the rise of cyborgs, beings that are part human, part machine. These augmented humans might possess enhanced cognitive abilities, greater physical strength, or even new senses that allow them to navigate the complexities of space. The merging of human and machine intelligence could lead to entirely new forms of consciousness, blurring the lines between biological and artificial life. In the distant future, the concept of mind uploading, transferring human consciousness in a digital form, could enable humans to explore space as purely digital entities. Freed from the limitations of biological bodies, these digital beings could travel across the universe, inhabiting robotic avatars or existing in virtual realities. This radical transformation of human life would raise profound philosophical questions about the nature of consciousness, identity, and what it means to be human. Interstellar exploration and the search for meaning. As humanity begins to explore other star systems, the existential questions that have long driven philosophers, theologians, and scientists will take on new significance. The discovery of intelligent extraterrestrial life, even if it is millions of light years away, would challenge everything we know about ourselves and our place in the universe. Are we alone, or are we part of a larger cosmic community? How would the existence of advanced alien civilizations impact our sense of purpose and meaning? In the absence of contact with other intelligent beings, the search for meaning in the cosmos will continue to shape our spacefaring future. As humans venture further from Earth, the experiences of seeing new planets, walking on alien worlds, and gazing at stars from another solar system will undoubtedly evoke a deep sense of awe, wonder, and humility. These experiences may lead to new forms of spirituality and philosophy, rooted in the knowledge that humanity is part of something far larger than itself. Space exploration will likely lead to a cultural renaissance, where art, literature, and music are inspired by the new frontiers of human experience. Just as the age of exploration inspired a wave of creativity and innovation during the Renaissance, the exploration of space could spark new artistic movements that reflect the profound beauty, mystery, and complexity of the cosmos. As we look ahead, it is clear that the future of humanity is not limited to Earth. The stars are our next destination, and the journey into the cosmos will challenge us to rethink everything we know about life, intelligence, and the universe. With each step into the unknown, we move closer to answering the most fundamental questions of existence. And in the process, we will transform not only our world but ourselves. The adventure of space exploration is just beginning, and the possibilities are as infinite as the universe itself. As we step further into the cosmic unknown, the expansion of humanity into space will reach unprecedented levels of complexity and scope, pushing the boundaries of our imagination and our technological capabilities. With each new achievement, whether it's establishing a self-sustaining lunar base, sending the first humans to Mars, or developing the technology for interstellar exploration, humanity's presence in space will evolve from tentative exploration into full-scale habitation and even dominance of the solar system. But with this expansion comes the need for profound changes in how we think, govern, create, and even define ourselves. The reality of living off-world, daily life in space colonies. As space colonies become a reality, whether on the Moon, Mars, or in space stations orbiting other planets, the routines and daily lives of their inhabitants will mark a significant departure from Earth's familiar patterns. The practicalities of space life will require humans to adapt to new rhythms of existence, from altered sleep cycles to different work-life balances, all shaped by the alien environments they occupy. For instance, living on Mars, where days are 24.6 hours long, may seem like a small adjustment, but the experience of Martian years, nearly twice as long as Earth's, will affect long-term planning, celebrations, and even how people mark personal milestones. Colonists may need to rethink familiar concepts like birthdays, holidays, and work weeks, as the passage of time in these new worlds takes on different meanings. In lunar colonies, where the day-night cycle lasts 29.5 Earth days, the inhabitants will have to find ways to cope with the long stretches of daylight followed by prolonged periods of darkness. Space stations or cities in orbit will need to develop artificial time systems to simulate a regular cycle of day and night, using technology to help inhabitants maintain a healthy balance between work, rest, and recreation. In these new realities, the structure of life will become more fluid, with technology playing a significant role in creating a sense of normalcy. The challenges of sustaining human life in space will extend far beyond mere physical survival. To create thriving communities, space colonies will need to support the mental and emotional well-being of their inhabitants. Isolation, limited social interaction, and the confined environments of space habitats could lead to psychological issues such as depression or anxiety. As a result, psychological support systems will be essential, with virtual reality environments, immersive entertainment, and advanced AI companions all playing critical roles in ensuring that colonists can stay connected to Earth, maintain their mental health, and foster a sense of community. AI governance and post-Earth societies. The governance of space colonies represents another profound shift that will take place as humanity extends its reach into space. On Earth, political systems are influenced by geography, culture, and historical precedent, but in space, these factors will change dramatically. Space colonies will require governance systems that can manage not just the survival of their inhabitants, but also the complexities of resource management, life support systems, and even interactions with Earth and other colonies. AI-assisted governance is one of the most promising solutions for the challenges of managing space societies. AI could play a critical role in organizing and overseeing everything from energy consumption and resource allocation to healthcare and environmental monitoring. Space colonies may experiment with new forms of political organization, such as direct digital democracies, where AI helps manage the complexities of decision-making by analyzing data, offering policy recommendations, and even overseeing the implementation of laws. AI could also assist in maintaining fairness and transparency in governance by providing a neutral, data-driven approach to complex problems, ensuring that decisions are made based on the needs of the entire colony rather than the interests of a select few. However, the rise of AI governance will raise significant ethical questions about the role of machines in human decision-making. How much autonomy should we grant AI systems in managing our lives? Should AI have the final say in decisions that affect human well-being, or should humans retain ultimate control? As these systems evolve, space colonies may develop entirely new political and social models, distinct from those found on Earth. The first space constitutions could be drafted, outlining the rights and responsibilities of colonists in these off-world societies. New ideas about citizenship, governance, and autonomy could emerge, particularly as space colonies become more self-sufficient and less reliant on Earth. Over time, the political identity of spacefaring humans could diverge from that of Earth-based humans, leading to the creation of post-Earth societies with their own laws, cultures, and values. Human evolution and adaptation in space. One of the most dramatic changes brought about by long-term space habitation will be its impact on human biology. While our bodies evolved in response to Earth's specific conditions, gravity, atmosphere, and the magnetic field, living in space will push human physiology to adapt in ways that are both fascinating and unpredictable. The effects of microgravity are already well documented. Astronauts in space experience muscle atrophy, bone density loss, and fluid redistribution within their bodies. While current missions typically last for months, long-term habitation on space stations, the Moon, or Mars will expose humans to these conditions for years, if not lifetimes. Space colonies will need to develop ways to counteract the effects of microgravity, whether through advanced exercise regimens, artificial gravity systems, or perhaps even genetic modifications that enhance human resilience to the stresses of space environments. Additionally, radiation exposure poses a significant threat to human health in space. Outside of Earth's protective magnetic field, colonists will be exposed to higher levels of cosmic radiation, which can increase the risk of cancer and other health problems. Future space habitats will need to include shielding from this radiation, using materials like water, regolith, or advanced synthetic compounds to protect their inhabitants. However, it's also possible that genetic engineering could be used to make humans more resistant to radiation, potentially editing genes to repair damage more effectively or to enhance natural defenses against cancer. Over time, these environmental factors could drive human evolution in space. If humans remain in space or on other planets for generations, the pressures of these environments, microgravity, radiation, isolation, may lead to speciation, with humans in different space habitats evolving to become distinct from their Earthbound ancestors. It's possible that the physical and psychological differences between Earth-based humans and space colonists could become so pronounced that they form entirely new branches of the human tree, leading to the rise of post-human species adapted to life beyond Earth. The new frontiers of science and technology. The technological innovations developed for space exploration will not only allow humans to survive and thrive in space, but will also have profound implications for life on Earth. Space-based manufacturing offers the potential to create materials that are impossible to produce under Earth's gravity. For example, crystals grown in the weightlessness of space are often more pure and perfect than those grown on Earth, with applications in everything from electronics to medical devices. 3D printing in space could allow us to manufacture tools, spare parts, and even entire habitats on demand, reducing the need for costly resupply missions from Earth. Similarly, space-based solar power could revolutionize energy production on Earth. Satellites equipped with large solar arrays could collect energy from the sun and beam it back to Earth in the form of microwaves or lasers, providing a continuous supply of clean, renewable energy. This technology could help solve the global energy crisis and reduce our reliance on fossil fuels, mitigating the impacts of climate change. Asteroid mining represents another game-changing frontier. Asteroids contain vast quantities of valuable metals, including platinum, gold, and rare earth elements that are essential for modern technologies. Mining these resources in space could provide an almost limitless supply of raw materials, reducing the need for environmentally destructive mining practices on Earth and opening up new opportunities for economic growth in space. However, this will also require the development of international space law to regulate the ownership and extraction of space resources, ensuring that they are used responsibly and equitably. One of the most exciting developments in space exploration will be the advancement of interstellar travel technologies. While we are still many years away from sending humans to other star systems, the development of fusion propulsion or light sails could one day enable us to travel to nearby stars, like Proxima Centauri, within a human lifetime. Breakthrough Starshot, a project that aims to send tiny, laser-powered probes to the Alpha Centauri system, represents the first step in this direction. These missions will provide us with valuable data about other star systems and may even help us identify planets that could be suitable for human colonization. In the more distant future, technologies like warp drives, which bend space-time to allow faster-than-light travel, may become a reality, enabling humanity to explore distant galaxies and perhaps even encounter alien civilizations. While warp drives remain speculative, research into the nature of space-time, dark matter, and dark energy may one day provide the insights needed to make such technologies possible. Encountering extraterrestrial life. One of the most profound events in the history of space exploration would be the discovery of extraterrestrial life, whether it's microbial life on Mars or Europa or intelligent life in another star system. Such a discovery would fundamentally alter our understanding of life, intelligence, and the universe itself. If we discover microbial life on Mars or beneath the icy oceans of Europa, it would suggest that life is not unique to Earth and may be common throughout the cosmos. This would raise profound questions about the origins of life and its potential diversity across the universe. Are we looking at life that shares a common ancestry with Earth-based organisms, perhaps seeded by comets or asteroids, or is it an entirely separate genesis? If we find intelligent life in another star system, the implications would be even more staggering. The discovery of an intelligent alien civilization would force us to reconsider the nature of intelligence and consciousness itself. How would we communicate with such beings? Would they share our values? Or would their thought processes be so alien that meaningful dialogue would be impossible? Could we learn from their technological advancements? Or would they see us as primitive by comparison? The ethical implications of encountering intelligent life are vast. Should we attempt to contact such civilizations? Or should we remain silent, fearing the potential consequences? If we engage with an alien civilization, what responsibilities do we have to ensure peaceful and respectful interactions? These are questions that will need to be addressed as we continue our search for life beyond Earth. The cosmic future of humanity. As humanity ventures deeper into space, we are not only exploring new frontiers but also reshaping our destiny. The challenges and opportunities of space exploration will drive profound changes in our societies, our technologies, and even our biology. The rise of space-based civilizations, the development of new forms of governance, and the potential discovery of alien life all point to a future where humanity's existence is no longer confined to a single planet. In this cosmic future, we will not only push the boundaries of science and technology, but also confront fundamental questions about life, consciousness, and our place in the universe. The adventure of space exploration is not just a journey of discovery. It is a journey of transformation, where humanity will evolve into something new, something greater. We are at the dawn of a new era, where the stars are not just distant points of light in the night sky, but destinations waiting to be explored. The possibilities are as infinite as the universe itself, and the future of humanity is truly beyond the horizon. As we delve deeper into the cosmic future of humanity, it becomes evident that the next great leap will not just be technological or even biological. It will be a philosophical and existential transformation. The exploration of space will push humanity to grapple with some of the most profound questions we have ever faced. What does it mean to be human in a universe that is no longer our sole domain? How will we redefine concepts like identity, morality, and society when the boundaries of Earth no longer define our existence? As we continue to expand into space, these questions will drive us toward new ways of thinking, living, and interacting with the cosmos. The philosophy of the cosmos, redefining humanity's place. Throughout history, humanity's understanding of itself has been shaped by our relationship with the Earth and the sky. Ancient civilizations looked to the stars for guidance and understanding, interpreting celestial patterns as signs from gods or as maps of fate. In the modern era, we have used science to unlock many of the secrets of the universe. But as we begin to live and work in space, our relationship with the cosmos will undergo an even more radical transformation. No longer will space be a distant, untouchable frontier. It will become our new home. This shift will spark a philosophical renaissance, forcing us to reconsider questions about existence, purpose, and meaning. For centuries, philosophers have debated humanity's place in the universe. But the realities of space colonization will turn these abstract debates into urgent, practical concerns. How will the experience of living on other worlds change our understanding of what it means to be human? Will the settlers on Mars or the moons of Jupiter develop their own unique philosophical traditions, shaped by the challenges and perspectives of life on those distant worlds? And how will spacefaring humans relate to Earth, the planet that gave rise to our species but may no longer be our primary home? For many, the act of living in space may foster a profound sense of cosmic humility. Seeing Earth from space, a fragile blue that's suspended in the vastness of the universe, has already inspired astronauts to feel a deep connection to the planet and a sense of responsibility for its preservation. As more humans experience space firsthand, this sense of interconnectedness may grow stronger, leading to new ethical frameworks that emphasize our duty to care for not only Earth, but the wider cosmos. This could give rise to a new form of cosmic environmentalism, where humanity is not just responsible for the Earth's ecosystem, but for the ecosystems of other planets, moons, and even interstellar environments. At the same time, space colonization may also give rise to feelings of existential isolation. As humans move farther from Earth, physically and psychologically, they may begin to feel a sense of detachment from their origins. The experience of living on a planet like Mars, with its barren landscapes and hostile environment, could foster a sense of alienation, both from Earth and from the rest of humanity. Over time, this isolation could lead to the development of new forms of identity, where space colonists see themselves not as Earthlings but as Martians, Lunarians, or spacefaring nomads. These new identities could be shaped not only by the practical realities of life in space, but also by the philosophical and spiritual questions that arise from living in a universe where humanity is no longer confined to one world. Cultural evolution, new art, music, and spirituality in space. The expansion of humanity into space will also drive a new wave of cultural evolution, as spacefaring humans develop new forms of expression, creativity, and belief. Just as the Renaissance in Europe was sparked by the exploration of the world and the rediscovery of ancient knowledge, the exploration of space will inspire a cultural renaissance that draws on the vastness of the cosmos for inspiration. Art and music, in particular, will evolve in response to the unique environments of space. Weightlessness, for example, will open up new possibilities for dance, sculpture, and other forms of artistic expression. Imagine dancers moving gracefully through zero gravity, or sculptors creating floating, three-dimensional works that defy the limitations of Earth's gravity. Sound in space, where there is no atmosphere to carry vibrations, will also inspire new forms of music that rely on digital synthesis vibration-based experiences, or even the use of radio waves and electromagnetic fields as mediums for artistic expression. In these environments, art and music will take on entirely new dimensions, reflecting the freedom and constraints of life beyond Earth. The spirituality of spacefaring humans will likely evolve as well. The vastness of the universe and the experience of living on other planets will inspire new forms of religious and philosophical thought, grounded in the realities of space travel and the exploration of alien worlds. For some, the cosmos may inspire a sense of cosmic spirituality, where the universe itself is seen as a living, conscious entity. Others may adopt more secular, existential perspectives, viewing life in space as a reflection of humanity's inherent drive to explore, survive, and thrive in even the most hostile environments. Existing religious traditions will likely adapt to the realities of space life, developing new rituals, practices, and interpretations to accommodate the unique challenges of space colonization. Prayers and meditations may take on new meanings when offered under the light of distant stars or in the artificial environments of space stations. Concepts of pilgrimage may evolve, with trips to Earth becoming sacred journeys for space colonists who seek to reconnect with their ancestral home. For those who seek spiritual meaning in the vastness of space, the search for extraterrestrial life may take on a deeply philosophical or even religious significance. The discovery of alien life, especially intelligent life, would fundamentally challenge many of the assumptions that have shaped human religious and spiritual thought for millennia. If we are not alone in the universe, what does that mean for our understanding of creation, divinity, and our purpose? Could contact with alien civilizations lead to the development of new, interstellar spiritual traditions, where humans and aliens share beliefs and rituals that transcend planetary or species boundaries? Alien encounters and the ethics of contact. The discovery of alien life, whether microbial or intelligent, will also force humanity to confront a host of ethical dilemmas. How should we interact with alien species, and what responsibilities do we have toward them? If we find microbial life on Mars or beneath the icy oceans of Europa, should we study it, protect it, or leave it alone? What happens if our efforts to colonize these planets pose a threat to these ecosystems, even if the life forms are not intelligent? These questions will become increasingly urgent as we expand our presence in the solar system and begin to explore exoplanets and other star systems. The possibility of encountering intelligent extraterrestrial civilizations raises even more complex ethical and philosophical issues. If we detect a signal from an advanced alien civilization, should we attempt to make contact, or should we remain silent, fearing the potential consequences? What if the aliens are more technologically advanced than us? Will they see us as equals, or as inferior beings to be studied or even exploited? Alternatively, what if we encounter a less advanced civilization? How should we interact with them? And what ethical obligations do we have to ensure that we do not harm or manipulate them? The idea of cultural imperialism will take on new significance in the context of space exploration. Just as Earth's history is filled with examples of more technologically advanced civilizations exploiting or oppressing less advanced societies, the expansion of humanity into space raises the possibility that we could impose our values, technologies, and social structures on alien species. To avoid repeating the mistakes of our past, we will need to develop new codes of ethics for interacting with alien life, grounded in principles of respect, humility, and cooperation. At the same time, contact with alien civilizations could also offer humanity the opportunity to learn from other forms of intelligence. Aliens may possess technologies, philosophies, or social structures that are radically different from anything we have developed on Earth. And these new ideas could help us solve some of the most pressing challenges we face as a species. By approaching alien civilizations with an open mind and a willingness to learn, we may be able to forge new alliances that benefit not just humanity, but the entire cosmos. Transcending the human, the rise of post-humanism and digital consciousness. As space exploration drives humanity toward the stars, we may also begin to transcend the limits of our biological form. Advances in genetic engineering, cybernetic enhancement, and artificial intelligence will offer humans new ways to adapt to the challenges of space, but they will also raise profound questions about what it means to be human. One of the most dramatic possibilities is the rise of posthumanism, where humans evolve into new forms of life that are no longer constrained by the limitations of biology. Genetic modifications could allow humans to survive on planets with extreme environments, while cybernetic enhancements could augment human abilities beyond anything we currently imagine. Over time, these changes could lead to the emergence of new species of humans, each adapted to the specific conditions of the planets or habitats they inhabit. Even more radical is the possibility of mind uploading, the transfer of human consciousness into digital form. In this future, humans could live as digital entities, freed from the limitations of the body and able to explore the universe in ways that biological humans cannot. These digital humans could travel vast distances across the galaxy, inhabiting robotic bodies or existing entirely in virtual realities. The rise of digital consciousness raises profound philosophical questions about the nature of identity and consciousness. If your mind is uploaded into a computer, are you still the same person? What happens if multiple copies of your mind are created? Are they all you, or are they distinct individuals? Can a digital consciousness experience the same emotions, thoughts, and sense of self as a biological consciousness? Or is something essential lost in the process of digitization? In a future where humans can exist as both biological and digital beings, the boundaries between life, death, and immortality may blur. Digital humans could potentially live forever, existing in virtual worlds, or traveling across the stars indefinitely. This raises new ethical questions about the value of life and the nature of existence. What does it mean to be alive if your consciousness is no longer tied to a physical body? And how will society evolve if some humans achieve digital immortality while others remain bound to the limitations of biological life? The ultimate frontier, humanity's cosmic future. As humanity moves deeper into the cosmos, we are not just exploring new worlds. We are exploring new ways of being. The challenges of space colonization, the discovery of alien life, and the rise of posthumanism will all force us to rethink our understanding of life, intelligence, and consciousness. In this new era, humanity's destiny is no longer tied to Earth. We are on the verge of becoming a multiplanetary species, and perhaps even a multidimensional consciousness, capable of exploring not just the physical universe, but the very fabric of reality itself. The future of humanity in space is as vast as the universe itself, filled with infinite possibilities for discovery, growth, and transformation. With each step we take into the cosmos, we are not only expanding our horizons, but also evolving into something greater than we have ever been. The stars are not just a destination. They're the next chapter in the story of humanity, a story that will be written across the galaxies for millennia to come. As we venture forth into the infinite, the only limits we face are the ones we choose to accept, and the future of humanity is as boundless as the universe that awaits us. As humanity ventures deeper into space, the journey into the cosmos will not merely be one of scientific exploration or technological advancement. It will be a journey of transformation that touches every aspect of human existence. The next great chapter in our evolution is not just about the distant worlds we will visit or the new frontiers we will conquer, but about the profound shifts in how we define life, consciousness, society, and our place in the universe. With each step forward, we will confront new challenges and opportunities that demand a rethinking of everything from ethics and governance to identity and existence itself. Becoming a multiplanetary civilization, a new chapter in human history. The reality of becoming a multiplanetary species represents a seismic shift in human history, akin to the greatest migrations and discoveries of our past. Colonizing the Moon, Mars, and potentially the moons of Jupiter and Saturn, or even free-floating space habitats, will fundamentally alter how we view ourselves. We will no longer be tied to the gravitational pull of a single planet. Our species will extend its presence across multiple worlds, each with its own unique environmental, social, and cultural conditions. The expansion of human civilization into space will require a new understanding of what it means to be human, as we will encounter environmental conditions unlike anything we have ever experienced on Earth. Mars' thin atmosphere and freezing temperatures, The moon's barren surface and weak gravity, and the extreme radiation exposure on deep space missions will shape human physiology and psychology in ways that are difficult to predict. Over generations, these colonies may develop distinct cultures, languages, and even physical adaptations, with space settlers potentially evolving to better suit their environments. This fragmentation could lead to the rise of planetary identities. Just as national identities arose from geographic boundaries on Earth, space colonists may develop a sense of identity based on their home planet or habitat. A Martian could have a very different outlook on life, society, and governance compared to someone who remains on Earth or who grows up in a space station. These new identities will not only be shaped by the physical differences between planets, but also by the social, political, and economic systems that evolve within these distinct environments. The social structures and governance of space colonies will be designed to meet the unique challenges of each location. Colonies on Mars, for example, may adopt cooperative governance models, where decision-making is driven by the need for survival in a harsh and resource-limited environment. Space colonies could experiment with new forms of democracy, meritocracies based on technological expertise, or even AI-assisted governance, where advanced algorithms optimize the management of resources and human well-being. The relatively small populations of these colonies could allow for more direct and participatory forms of governance, where every citizen has a say in critical decisions. As humanity spreads across multiple planets, new alliances and federations could emerge, potentially leading to the formation of interplanetary unions or coalitions. These federations would not only manage trade and resources between planets, but also mediate disputes, foster cooperation on scientific research, and ensure the equitable distribution of space-based resources like water, minerals, and energy. The creation of a space federation could echo the formation of nation-states on Earth, but would also have to consider the vast distances and communication delays between worlds, as well as the differing environmental needs and priorities of each planet. Cosmic ethics. New moral challenges in a multi-world reality. As we move beyond Earth, we will encounter new ethical dilemmas that require us to rethink our relationship with other planets, alien ecosystems, and potentially intelligent life. The expansion of humanity into the cosmos will be accompanied by profound moral questions about our responsibilities to the planets we inhabit and to the life forms we may discover there. One of the first ethical challenges we will face is the question of terraforming. On planets like Mars, where the environment is hostile to human life, many have proposed using advanced technology to alter the planet's atmosphere, temperature, and surface conditions to make it more Earth-like and habitable for humans. But what are the ethical implications of fundamentally altering another planet's ecosystem, even if it appears to be lifeless? If we discover microbial life on Mars or in the oceans of Europa, do we have a right to terraform and potentially destroy these ecosystems? Or should we prioritize their protection, even if it limits human expansion? The question of planetary protection, the idea that we have a moral obligation to preserve alien environments from contamination by Earth-based life, will become even more pressing as we expand into space. Current planetary protection policies are designed to prevent biological contamination of other planets during scientific exploration, but as we begin to establish permanent settlements, these policies will need to be reevaluated. Should we allow the introduction of Earth-based organisms into alien environments if it means making these planets more habitable for humans? How do we balance the need for human survival and expansion with the potential destruction of alien ecosystems? The potential discovery of intelligent extraterrestrial life will raise even more profound ethical challenges. If we make contact with an advanced alien civilization, how should we interact with them? Should we attempt to communicate? And if so, what are the moral principles that should guide our interactions? What if the alien civilization is less advanced than ours? Do we have a responsibility to protect them from exploitation or interference? Or should we avoid contact altogether to preserve their way of life? These are not just scientific questions, but deeply moral ones that will shape humanity's future as we venture into the unknown. Human augmentation and evolution in space. As humans adapt to the challenges of living in space, we will inevitably turn to human augmentation and genetic engineering to enhance our bodies and minds. The extreme environments of space, such as the microgravity of space stations or the high levels of radiation on Mars, pose serious health risks, but advances in biotechnology could allow us to modify our bodies to better suit these conditions. For example, genetic engineering could be used to enhance human resistance to radiation, allowing future generations of space travelers to live on Mars or travel through deep space without suffering the harmful effects of cosmic radiation. Similarly, cybernetic enhancements, such as artificial limbs, neural implants, or even augmented vision, could help humans perform tasks that are impossible in the challenging environments of space. Over time, these enhancements may become so integrated into human biology that the line between natural and artificial will blur, leading to the rise of post-human or transhuman identities. This evolution of the human body and mind will be accompanied by a parallel transformation in human society and culture. Spacefaring humans may develop new values and beliefs that reflect their enhanced abilities and their new relationship with technology. Concepts like human identity, consciousness, and selfhood may evolve to accommodate the blending of biological and artificial components. In this future, posthumanism, the philosophical belief that humans should evolve beyond their current biological and cognitive limitations, will become a central debate as we redefine what it means to be human. The ethical implications of human enhancement will also come to the forefront. Should we allow genetic modification and cybernetic enhancements for everyone? Or will these technologies be limited to those who can afford them, creating new forms of inequality? What are the long-term consequences of altering human biology on such a fundamental level? As we develop the ability to modify not just our bodies but our brains, will we still be the same individuals we once were? Or will these enhancements create entirely new forms of consciousness and identity? Interstellar exploration, the final frontier. While our expansion into the solar system is the first step toward becoming a multi-planetary species, the ultimate goal of space exploration is to travel beyond our solar system and explore the stars. Advances in propulsion technology, such as nuclear fusion, antimatter engines, or light sails, will eventually allow us to travel to nearby star systems like Alpha Centauri, where we may discover habitable exoplanets or even alien civilizations. The journey to the stars will represent the greatest challenge humanity has ever faced. Interstellar travel will require us to solve problems that seem insurmountable today. How to sustain life during journeys that could last decades or centuries, how to maintain communication across vast distances, and how to ensure that future generations of space travelers remain motivated and focused on their mission. One possible solution is the creation of generation ships, massive spacecraft designed to house multiple generations of humans who will live, work, and reproduce aboard the ship as it travels toward its destination. These ships will need to be entirely self-sustaining, with closed-loop ecosystems that provide food, water, and air for the inhabitants. Over time, the inhabitants of generation ships may develop entirely new cultures and social structures, shaped by the unique environment of life aboard a spacecraft traveling through deep space. Another potential solution is the development of cryogenic sleep or biostasis, where space travelers are placed in a state of suspended animation during their journey, allowing them to wake up at their destination without aging. This technology could revolutionize interstellar travel, reducing the need for generation ships and allowing humans to travel vast distances in a single lifetime. Interstellar exploration will also require us to think in long-term timescales. The journey to even the closest star systems could take decades or centuries, and the decisions we make now will have consequences for future generations. How do we maintain the continuity of missions that span multiple human lifetimes? What ethical responsibilities do we have to the future generations who will complete the missions we begin? These are questions that require us to think beyond the immediate and consider the long-term survival and success of the human species, the singularity and the ultimate future of humanity. One of the most radical ideas about the future of humanity in space is the concept of the technological singularity, the moment when artificial intelligence surpasses human intelligence, leading to an exponential acceleration in technological progress. Some futurists believe that the singularity could occur within the next few decades, transforming every aspect of human life and making it possible to solve problems like interstellar travel, immortality, and even the creation of new universes. In a post-singularity world, superintelligent AI could help us unlock the secrets of the universe, allowing us to travel faster than light, manipulate space-time, or even upload human consciousness into digital form. In this future, humans might exist as digital beings, capable of exploring the universe without the limitations of biological bodies. Virtual worlds could be created where humans experience life in ways that are impossible in the physical universe, and the boundaries between reality and simulation could become meaningless. The singularity also raises profound questions about the future of human consciousness. If AI becomes vastly more intelligent than humans, what role will we play in the future of the universe? Will we merge with AI, becoming part of a new form of intelligence that transcends biological life? Or will we be left behind as AI explores the cosmos on its own? These are questions that touch on the very essence of what it means to be conscious, to be alive, and to have a purpose. As we look toward the ultimate future of humanity, we must consider not only the practical challenges of space exploration, but also the existential questions that will define our place in the cosmos. The journey into space is not just a quest for new worlds. It is a quest for new ways of being, new forms of life, and new understandings of the universe. The future of humanity is infinite, and the stars are only the beginning. With each step we take into the unknown, we move closer to unlocking the deepest mysteries of existence and becoming part of the vast, cosmic story that has only just begun to unfold. The adventure ahead is boundless, and the possibilities are as endless as the universe itself. As humanity continues its quest into the depths of the cosmos, the horizons that lie ahead are not just physical, but intellectual, emotional, and existential. Every leap forward in space exploration, technological enhancement, and the encounter with new worlds will force us to question and redefine who we are, what we value, and what it means to be human. The adventure into the stars will become not just a voyage of discovery, but a profound journey of self-reflection. With each step into the unknown, we will unlock new layers of our own identity, challenge our understanding of life, and face dilemmas that stretch beyond our current moral frameworks. The expansion of consciousness, mind, identity, and post-human evolution. One of the most extraordinary consequences of space exploration and technological advancement will be the expansion of consciousness itself. As humans continue to integrate artificial intelligence, AI, advanced neurotechnologies, and genetic modifications into their bodies and minds, the boundaries of human identity will begin to dissolve. What once defined us as human, our physical bodies, biological constraints, and even our individual consciousness, may become fluid, adaptable, and ultimately transcendent. One of the most radical ideas at the frontier of human evolution is the concept of consciousness uploading. This would involve transferring a human mind into a digital substrate, allowing an individual's thoughts, memories, and personality to exist independently of the biological body. This transformation could allow humans to live indefinitely in digital form, free from the limitations of aging, disease, or physical harm. These digital beings could inhabit virtual worlds of their own creation, exploring new forms of existence and interaction that are impossible for biological humans. This technological possibility leads to a host of existential and ethical questions. What happens to our sense of self when we can exist as both biological and digital entities? If multiple copies of a person's consciousness are made, are they all the same person, or do they become independent individuals with their own thoughts and experiences? The ability to modify and enhance one's mind could also lead to divergent forms of consciousness. Some humans might choose to remain fully biological, while others might enhance their cognitive abilities with AI implants or become entirely digital. This could lead to new social dynamics and even new species of post-humans, each with its own culture, values, and worldview. As humans begin to exist in both physical and digital realities, the concept of identity will become increasingly complex. Today, identity is closely tied to our bodies, our memories, and our experiences. But in a future where consciousness can be transferred between biological, digital, and synthetic forms, identity could become a fluid and dynamic concept. A person could exist in multiple forms simultaneously, with different aspects of their personality manifesting in different realities. The boundaries between self and other, human and machine, and individual and collective consciousness could blur, creating entirely new ways of experiencing and understanding existence. Digital immortality and the ethics of eternal life. The possibility of digital immortality, where a person's consciousness can be preserved and potentially live forever in digital form, raises profound ethical and philosophical questions. On the one hand, the ability to achieve immortality could allow humans to transcend the limits of biological life, offering endless opportunities for exploration, creativity, and growth. Individuals could live for centuries, witnessing the evolution of human civilization and the expansion of humanity into the stars. However, the concept of immortality also brings with it significant challenges. Would eternal life lead to stagnation or boredom, as individuals exhaust all possible experiences? Would the pursuit of immortality create a society where death is feared and avoided at all costs, leading to new forms of inequality between those who can afford digital immortality and those who cannot? In this future, death may no longer be seen as an inevitable part of life, but rather a choice, one that individuals must grapple with as they navigate their own sense of purpose and meaning. Moreover, the rise of digital immortality could challenge traditional ideas about legacy and the passing of knowledge. Today, the cycle of birth, death, and the transfer of wisdom between generations has shaped the course of human history. But in a world where individuals can live indefinitely, how will societies evolve? Will the old guard cling to power, unwilling to pass the torch to younger generations? Or will new cultural norms emerge that encourage individuals to explore different forms of existence, allowing them to reset their lives by transferring their consciousness into new bodies, environments, or realities? The ethical implications of immortality will extend beyond the individual, shaping the development of human civilization itself. How do we ensure that digital immortality is accessible to all, rather than just the wealthy elite? Should there be limits on how long a person can live in digital form, or how many copies of a person's consciousness can be created? These questions will need to be addressed as we grapple with the consequences of overcoming the biological limitations that have defined humanity for millennia. The encounter with alien civilizations, bridging worlds, minds, and cultures. As humanity continues its exploration of the universe, one of the most profound events in history could be the discovery of intelligent extraterrestrial civilizations. Such an encounter would force us to reconsider our understanding of life, intelligence, and consciousness on a cosmic scale. What if alien life forms exist, but their intelligence is so radically different from ours that communication is nearly impossible? How would we establish meaningful contact with beings who may not share our biological makeup, our modes of perception, or even our concept of self-awareness? If we encounter an alien civilization that is more advanced than ours, we may find ourselves in a position of cultural and technological inferiority. How we approach this relationship, whether with fear, humility, or a willingness to learn, will shape the future of humanity's role in the cosmos. Aliens may possess technologies and philosophies that are far beyond our understanding, offering us new ways to think about existence, ethics, and the universe itself. They may also have faced challenges similar to those we face today. Questions about sustainability, artificial intelligence, and the balance between technological advancement and environmental stewardship. By learning from their experiences, we could gain invaluable insights into our own future. Don't forget to subscribe in the channel and like the video for more.